Hey everyone, we're going to jump into it here and actually start reviewing the formula sheet. So let me write this down here. The first topic of the day is, so let's do Stat 201, Test 3. Well, this is all everyone knows is the review for the final. So let's go here and say Exam 3 formula sheet. Okay, this is the Exam 3 formula sheet. We're going to have MuBot send us to the review page. MuBot knows where the review page is at. So let's go ahead and have MuBot send us. My hair's getting so long. It's like in my face. It's in my eyes. Let me do this here. MuBot, send us to that review page. There we go. Thank you, MuBot. So he's a good MuBot.
You're welcome, Brian. This is the exam review page. People are confused. MuBot must go.
That's MuBot. He's the one who helps us out every day in class. So with this in mind, let's go over here to the formula sheet, and you can find it here on the exam review page. We're going to take a screenshot of it, and then we're going to start marking on it. We're doing each topic for about 25 minutes, and we're going to try to hold to that. And with the 25 minutes, we will then switch topics to another topic. So here is the formula sheet, and let's go through and tell you what everything is. Okay, so first off, let's talk about what there is on the formula sheet that can help you out, and you can get points on the test from it. It literally tells you the degrees of freedom. So the degrees of freedom are used to tell us the shape of the t or the chi-squared in this class. So here are the 3 times you see the degrees of freedom. And maybe we'll do this one a slightly different color right here because this is a chi-squared. Good to see you, Talon, right there. And so this is the chi-squared. Chi-squared can look a little bit different, usually right-skewed. The t distribution is more like the normal and rises up into the normal as it gets more degrees of freedom. So here are the 3 times you see the degrees of freedom for you. The 1 sample t is n minus 1 degrees of freedom. The 2 sample t is too complicated. We'll show that 2 sample t degrees of freedom formula, but we never solve it. We use applets, so you will not do it on the test. So the 2 sample t degrees of freedom formula is the following formula. That is the formula you are seeing right there in yellow. And if you have questions, feel free to ask. This is a stream where you can definitely ask any questions you have, but this is the formula that we never solve by hand. It's the 2 sample t. And we like to say it is too complicated. That's our mnemonic for remembering the 2 sample t. And the formula sheet just tells you, we'll tell you it. We'll tell you the degrees of freedom. So next you have at the very bottom right here, the chi-squared degrees of freedom. The chi-squared degrees of freedom circled here in green and highlighted in green is going to be rows minus 1 times columns minus 1. And this is one of my favorite ones to do because if anyone's in the chat and wants to answer this, if you have a grid right here of maybe we have on or off campus and we have people's favorite spot to go eat, McDonald's, Wendy's, or Burger King, what would the degrees of freedom of this be? And it's using this right here where it says degrees of freedom is rows minus 1 and columns minus 1. And Alice right there, got it, great answers. It is 2 degrees of freedom because this is a 2 by 3 and you delete 1 row, 1 column, and you get 1 by 2. That tells you the shape of the chi-squared is going to be somewhat like this. The degrees of freedom would be this is a chi-squared with 2 degrees of freedom. So you put the degrees of freedom down there at the bottom. That's where you put the degrees of freedom. Chi-squared with 2 degrees of freedom. So pretty easy as a ride. Great work right there too. And ask questions if you got it. We're going to switch topics every 25 minutes or so. Right now we're doing the formula sheet. And we basically talked about the free and easy things to know on it that tells you the degrees of freedom. So let's start from the beginning of the formula sheet, a very good place to start. The first thing you see right here are tests for proportions. Let me raise it up a little. Well, we'll keep it down here and I'll only appear for a second on the screen. I do love the formula sheet, but, there's the but, right? The way in which we give you the standard errors is not how I prefer. So if you look at the way this is written, this right here equates to the following. P hat plus or minus Z star, and we'll talk about what this all means in a second. You see where it says standard error? The standard error is this quantity right here. So you get P hat Q hat over N square root. And so this, I think it's worded a little bit weird. I wish we just put it in right here. We've just kept the standard error over there to the side. And this is the standard deviation, which would be down here on the bottom. So once again, if you write this other formula, writing the other formula is going to be p hat minus p naught over p naught q naught over n square root. And you just kind of see with my highlighting what goes where. Notice how that we're using this formula right here, and that's going to be way too big of a marker. It's this formula right here being used. So it's just plugging into it the standard deviation of p hat. And we will not test you on this, but there's a small difference between the standard deviation, or we never have. I can't promise. Highly unlikely we would ask you the small difference between the standard error, which is based on a sample, p hat, q hat, versus the standard deviation, which is based on assumed truth, p naught, q naught. So that's the small change in wording of standard error, which is a measure of uncertainty in your estimate of p hat, and also standard deviation, which is an amount of uncertainty based on a true belief, a true hypothesis. So let's mention what this notation is right here. And for each of these, we're going to give an example. We'll start here with the one that I'm not blocking right now, and we'll give p hat. We're going to highlight this in blue. What is p hat? Well, p hat is x over n. You'd have to hear something like 2 people out of 5 own cats. So what would be x in this example? If I say 2 out of 5 people own cats, what would be x in this example? Does anyone know? I'll answer a lot of questions today, but feel free to play along and answer questions. Great jobs, right? It'd be 2. So x equals 2 and n equals 5, and p hat equals x over n, which is 2 over 5. So p hat is equal to 40% or 0.40. Now q hat is the complement of p hat. Q hat and p hat always add up to 1. So once you find p hat, you just subtract from 1 and you get the following. You can also do it in your calculator just to double check, but you should hopefully see that those add up to 1. 1 minus 0.4 is q hat right there, and p hat and q hat up to 1. N is the sample size. It's how many observations we have. And then z star, which z star is going to be related to how confident we are. So I'm running out of room on this one. Really, move away real quick. Z star is going to be good to see page. If you are 68% confident, Z star is equal to 1 for 68. If you are, I'm going to bring back the formula sheet or watch this. Okay, good. Good. If you are 95% confident, then technically Z star is equal to 1.96, very close to 2. If you are 99.7% confident, Z star is equal to 3. So the Z star is the amount, does that make sense to everyone? The Z star is the amount of area you cover. It's related to the Z score relative to how confident you are, going from, usually we say 68, 95, 99.7. So the more confident you are, the bigger the Z gets. So we usually give you this on a test. There's a bunch of classic ones like 1.645 is 90%, 80% is 1.2816, 99 is 2.5758, 98 is 2.3263. I've memorized a bunch of them. How did you get 1.96? It's basically 2, and it's a number a lot of statisticians know. You know, when we did the 68, 95, 99.7 back in chapter 5, that's where the 1.96 basically comes from. It's basically 2, but 2 is a little too far. The truth is it's 68.26, 95.449, and 99.73. So that would be 1, 2, and 3. You don't need to memorize them. Here's a key thing to know. Great questions. Please ask them in the chat. A key thing to know is we would give them to you on the test. And the more confident you are, I'm going to highlight this in blue. The more confident you are, the wider the interval will get. The more confident, when you go from 68, 95, 99.7, thus increasing the z-score from things like 1, 2, or 3, the interval gets wider. It also gets less what? Because it's getting wider, it's getting less what? The interval's getting wider, and it's getting less what? Great answer, Thomas and Zariah. It's getting wider and less precise. You could increase precision by increasing the sample size. Increasing sample size, great job, Paige. Increasing sample size also makes it more precise, but doesn't change the confidence level. So the Z star controls the confidence level, and you get to pick it, whether you make a 90, 95, 80, 70, 60, 99. The more confident you are, the wider it gets, and the researcher picks how confident they want the interval to be. So let's this sheet's gone crazy. Let's do a new clean sheet right here. And let's talk about the test down here. Well, you wouldn't. That would be with the conditions right there, Zariah. You don't really make it more normal by changing the confidence or the sample size. Technically, sample size might be connected to that a little bit with success failure condition, which is the third condition to do these. You'd have to have random data, less than 10% of the population, and also at least 10 successes, at least 10 failures to do this part of this. And really good review right here to know the conditions also for this. So here is the testing portion. And what we have here for the testing portion right here is going to be p hat, which is what we saw in our sample, minus p naught. The top of every test is always a what between two values. Think of a D word. The top of every test, which you can see on other tests, is always a what. You can see it right there. On every test, it's always the what between two values when we do it. It's always going to be a difference. So the top of a test looks at the difference between two values, and then what do we do to that difference? We standardize that difference. So we go down here and we do the standard deviation of p hat right here, and it's p naught times q naught over n square root, and this is equal to a test statistic z. Now it's important to note that this z right, really, let me zoom out. This z right here is not, these are not each other, they're not. Let me write no, they are not the same thing. This is a z-score found by standardizing the difference. This is one you pick based on how confident you are. Same thing goes for this t down lower. This t and this t are not the same. This t and this t are not the same. The t up top is going to be based on how confident you are, where the t down low is based on the standardized difference. The t up top is based on your level of confidence you pick, and the t down low is the standardized difference. So with this in mind right here, what are these notations? Well, on these types of questions, you'd have to be doing something like, let's see if 75% of UT recycles, which is one of the questions on the practice test. Check out the practice test. And so if you are testing to see if 75% of UT recycles, what notation is that in here? It's like a researcher. Hey, good to see you, Colin, in the chat. So if you're trying to see if 75% of UT recycles, would that be Q naught, N, standard deviation P hat, P naught, P hat, Z P hat? What would it be? What would it be if you want to see 75% of UT recycles? Well, if you're testing it, you're seeing if that's true. That is the hypothesized true proportion. So if you are testing to see if 75% of UT recycles, it would actually be P naught. If you're trying to see if it's true, it'd be P naught. P hat is what you observe in a sample. P hat will always be found with X over N, so you need to have a sample, and then you need to look at the amount of successes in a sample. Like 5 out of your 12 friends own puppies. I guess that would be, got to think what that'd be, I should know. I think it's 41 point, is it that? Let's find out. 5 out of your 12 friends own puppies. I should know this. Hey, we got it. Good deal. So that is what it would be. You could do it as a percent, or you could do it as a decimal. So P naught it's what you assume is true according to the null. It's what you hypothesize. Anytime you see this little naught on it, that little ot is going to be hypothesized according to the null, like the true mean that we hypothesize is true down there. So the little naught on it is associated with the null hypothesis. So the true proportion is equal to what we hypothesize the true proportion to be. Or in another example, you could say the true mean, down for the next one, is equal to what we hypothesize the true mean to be. So this little naught right there is associated with this, and it's hypothesized according to the null. So it's the hypothesized truth. So questions would say something like, we believe 75% of UT recycles. So the null would be that the true proportion of UT that recycles is equal to 75%. And that makes that P naught. Then if we see 5 out of 12 students recycle, well, 5 would be X, and N would be 12, and P hat would be 41.66. Or as a percent. We multiply it as a decimal, so make sure you use it as a decimal. And Q naught, well, if P naught is equal to 0.75, what is Q naught? Well, Q naught is 1 minus P naught. They are complements of each other. So always remember that these two, when added up, equal to 1. P naught and Q naught equal to 1. And I think that explains everything right here. We have P hat, the sample size, P hat, the sample proportion, N, the sample size, X, the amount of successes in a sample. Standard deviation of P hat measures the variation within the sample proportion, P naught, the hypothesized true proportion, Q naught, the complement of the hypothesized true proportion, and then also ZP hat, which is going to be the standardized difference from what we saw in a sample to the hypothesized truth when we standardize by the standard deviation. Okay, just a few more tests to go, and we're doing great on this. We're going to try to do everything in like 25, 30 minutes and then change topics. Feel free to put the next topic you want in the chat. We're doing the whole formula sheet right now so people can see how it works and what's on it. Next, we get down here to working with the mean. What's our saying? Does anyone know about Mr. T? We love Mr. T, but we have a saying in our class. Mr. T is mean if you're doing drugs. If you're not doing drugs, he's probably a super nice guy. But if you're doing drugs, you're 80 PSA announcements. Mr. T is mean. So why do we say that? Well, anytime we're dealing with the mean, look at right here, it says the mean. Well, when you see means, you're dealing with T. So you see T. Mr. T is mean if you're doing drugs. So I never want to disparage the great Mr. T. Really one of my 80s heroes. So with this in mind, you can see right here we've done the same thing by breaking apart these formulas. So this is the standard error. Standard error is the same thing for both of these equations. So I guess I'll highlight it using the same color. You will plug in the standard error and you will get here y bar. Good to see you, Tiffany. Plus or minus the t star with n minus 1 degrees of freedom. Notice the degrees of freedom are right there. It tells you the shape of the t. And then the standard error is s over square root of n. I'll highlight each one as I say it. If you have a problem, this is how it would look right here. We saw that the average student spends $12 at Taco Bell. The variation within how much students spend at Taco Bell was $3, like away from the mean. So that would be the variation. The standard deviation for the sample was this. We talked to 200 students. That would be the sample size. And then here, the T star would be based on how confident we want the interval to be. We want to build a 98% confidence interval. Now, if we talk to 200 students, what are the degrees of freedom? So if we talk to 200 students, what are the degrees of freedom for the one sample T to estimate how much they spend on Taco Bell? Notice how much they spend on Taco Bell is going to be a quantitative question. So if we want to do a quantitative interval, we have to use a T interval. So how much do they spend on Taco Bell is means the average amount spent. And so it'd be 199 because n minus 1. The one sample T has n minus 1 degrees of freedom. And we're going over here to the T applet. And take a look at this. Let's say we want to build a 95% confidence interval. Well, we type in 199 and we do between, and we get very close to that famous 1.96. And that's because the T merges into the Z at higher and higher degrees of freedom. If I show you some more decimals right here, you'll see it's approaching 1.96. I can make it approach faster by adding more numbers to it, but at higher and higher degrees of freedom, the T becomes the Z. At very low degrees of freedom, it's very different. So the T created by William Gossett, working at Guinness Beer, true stories, is basically the normal, but corrected for sample size. My favorite degrees of freedom is actually 60 because at that point, it's basically 2, which is our 68, 95. 95% confidence interval is basically a T-score of 2 with 60 degrees of freedom. You will not have to find these values on the test. We will usually give you the T, but we want you to understand theoretically. Like you'll have to find this stuff, but you won't use the applets on the test. I want to make that very clear before someone says, you don't have to find values on the test. No. You don't have to use the applets on the test. We will make sure you can solve any question without using an applet. We'll give you the necessary tools. So that T star right there is based on the degrees of freedom, telling us which T we're using. That is subscript. It's not a multiply. And the star means based on a confidence level. This is a confidence interval right here because it has the classic components of a center, which is our best guess. That's the center. And then plus or minus the margin of error for the confidence intervals. That's our confidence interval. The next part of the formula sheet gives you the test, which is going to be the top of every test. We said it a moment ago, is a difference. Notice how you're just taking what you saw in your sample mean, subtracting the hypothesized truth. Then what do? You divide by the standard error, which standardizes the difference. This turns into a T with n minus 1 degrees of freedom. Notice, it does not have the star on it. It does not have that star, meaning it's different. You are solving for the standardized difference here. You are not picking the t based on how confident you want the interval to be. So you pick this t up here based on your level of confidence. You could just build a 99% confidence interval with 199 degrees of freedom. Down here, you do not pick the t. It is solved by the standardized the standardized difference. This is the difference between your sample mean. You saw in your sample a sample mean of 12, and you expected to see a mean of 8. Your standard deviation was 3, and your sample was 200, using very similar numbers to before. You saw an average of 12. You expected an average of 8. Your standard deviation was 3, and you had a sample size of 200. So that is the one sample t. Let's talk about the two sample t now. The two sample t is used to compare the means of two groups and look at their difference. Think of when you think two sample t, you're having two samples, which means you have two means. Now, here's a classic question people get wrong. What kind of data does a two sample t deal with? QQ, CC, or QC? As in quantitative, categorical, or quantitative categorical. What kind of data does a two sample t deal with? What kind of data? Well, if we're dealing with quantitative, we're actually building a scatter plot. Very common, don't worry. So this would be QQ. Categorical is a mosaic plot, which is the chi-squared test of independence. So the top one is going to be regression. The next one is the chi-squared. And then this one down here is where we have side-by-side box plots. If you have a two-level categorical X, you'd have two groups. And this is where you're looking at the difference between mean 1 and mean 2. Those might look like medians. It is QC right there, and that's where we do the two sample t. So you're comparing it. This is if you have two groups. The test changes if you have more groups. But the two sample t compares the means of two groups. And hopefully I've answered the question, but the y between is just the difference between them because we want to see, is there a difference between the two means? So we analyze that difference in the two sample t. So now, I'm out of a million word documents. We've seen this before. This part of the equation right here is actually this. It's the same thing here as is here. Let's write the equations lower. Exactly. That's where the categorical comes from because it's two groups. Mean of group 1, mean of group 2. And so it's not two quantitative variables. So you think means are quantitative. Well, the y variable is quantitative because that's what's on the y-axis for a box plot. But then the x is categorical right there. We just saw it a second ago that the x is categorical. You can see it over here behind me. So the x would be categorical because you have group A and group B. And then you'd have a quant y because you're looking at box plots right there on some quantitative scale. So that's why it's the difference between the means for two groups. And so now we're going to write these equations, y bar 1 minus y bar 2, which is literally the difference between the two means, plus or minus. That's where the margin of error starts. Everything after the plus or minus is a margin of error. T star, the star means you pick it based on degrees of freedom. It has that complicated degrees of freedom formula that we're not going to have you solve. Square root, and this is where we reach the standard error, s sub 1 plus n sub 1, s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. I'll write it correctly, I might say it wrong. If you look at the components of the interval, the test is very similar because the test is going to be y bar 1 minus y bar 2, and then we divide by the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And this is equal to a t, and we want to point out once again that these two t's are not the same because the t up top is going to be based on how confident you are, and the t down low is based on the standardized difference, the difference up top standardized. And so when you look at this, you would have a mean for group 1, like students scored an average in class 1 of 90, and in class 2 an 80. Then we want to build an 80% confidence interval. And so that's where this would come from. You'd find the correct t-score for the 80% confidence with the right amount of degrees of freedom. And that's correct, Thomas, depending on what we ask you to do. Good question. We could look at, feel free to ask what you want to do next, but you have to look at what is the question asking me to do. And then next, you can see right here the standard deviation of group 1, the standard deviation of group 2, the sample size of group 1, the sample size of group 2. Like within the class 1, the variation was 4 points. We had 200 students in class 1. Within class 2, there was a variation of 3 points and 200 students. Next, we get here to the two-sample t-test. You would take the mean of group 1, 90, minus the mean of group 2, 80. That's what the wide bars are. Then the standard deviations of like 3 and 4 for the variation within each group. Correct. Sample sizes do not have to be the same. I think I might have said they were the same for this imaginary problem, but you could have 80 students in this class and 200 students in this class. And we're just pretending you have two classes, class A, class B. And then you get a t-statistic here, which is the difference between the two means standardized. And that's the two-sample t-test right there. Mean 1, mean 2. The t picked on how confident you are related to the right degrees of freedom. Standard deviation 1, standard deviation 2. S would be the standard deviation. So it'd be like the standard deviation of class 1 was 3. Please, Elise right there, thank you for asking. So ask every question, and I'll try to answer them all. So S1 would be the standard deviation of group 1. S2 would be the standard deviation of group 2. N1 would be the sample size of group 1. N2 would be the sample size of group 2. Any questions about the two-sample T before we go on to the next one? We're going to change topics about every 30 minutes. We'll take like a 3 to 5 minute break between each one. The last one we have right here is the chi-squared test of independence. The chi-squared test of independence is used to test two categorical variables. And the thing I love about it is if we're testing like eating meat and passing the test, let's say burger, like you ate a burger the night before the test, like burger. I just want a burger. I used to go to Cookout all the time. Not good for your diet, but good food. So, and then pass the test, yes or no. So let's say eating a burger the night before the test, and whether or not someone ate a burger, what is the null hypothesis? So when you see here chi-squared test of independence, this is the easy way to remember the null. All you have to do is put that word independent between the two of these. So the null would be eating a burger is independent of passing the test. What does that mean? Rock knows.
It doesn't matter.
It doesn't matter. If you ate a burger, you're no more likely to pass the test than not pass the test. So notice this is two categorical variables to do the chi-squared test of independence, and you're trying to see if they're independent or the alternative, they're not independent, meaning there's an association. So what we have to do right here is we have to take what we see in the data and find out how far it is away from what we expect. And getting these values, we look at the counts exactly. How many individuals did we count in each group? So the observed would literally be something like, I saw that there were 40 students had burgers and passed, and there were 10 students who did not have burgers and passed. 50 students passed the test. 20 students failed the test out of the 70 because the numbers have to add up. And there were 10 students here, and then this would have to be 20. Is that right? I think, no. My numbers are off. I'm trying to make right numbers right here. If there's only 20 students there, I might not be able to make it work. So 20 students, and then that has to add to 70. So we could do 30. Well, no, it's not gonna add up. It should add up. It's like a brain teaser, and my brain's just not running at full steam right now. So this would have to add up here. So if there's only 20, I think I've like locked the numbers. It should be able to add up. Let's see here, 50. Oh, wait. And 20. There we go. And 10 and 10. There we go. Exactly, Zerai. I don't know why my brain just said nope. And this is how many you see. You see, wow, look at this. A lot of the students who ate burgers passed the test versus those who ate burgers and did not pass the test. Only 20 students failed, but of the students who passed, it was 80% of them eating burgers. We can look at this with a mosaic plot right here, and you would see the burger eating no versus yes. Well, the people who ate the burger, which is yes, if we look across here, you can see had an 80% pass rate. Does that make sense? 80% of the students who ate burgers passed versus the no not eating burgers. Of the students who did not eat burgers, only half of them passed. So half the students who ate burgers, or did not eat burgers passed versus 80% who ate burgers passed. And we're trying to ask, is this a big enough difference right here to say there is an association? So we have to find the expected counts. The expected counts are going to be another matrix we have to make, and we have to do row total times column total over grand total. So the row total is going to be the total for the row. That's the wrong one. Well, there's row total times column total. And then over the grand total, which is down here. There we go. And you can circle the numbers and multiply. And that'll get the equation 50 times 50 over 70. So that should be 2,500. So it's going to be like, I think 33 or something. 50 times 50 divided by 70. 35.7. So you would expect, really? Huh? Surprised that high. Let's go 36. I would not round this. Well, 35.7. And then we can actually solve for the other ones due to the degrees of freedom here being 1. But this would be 14.3. And this would be 6.7. And we can check the math here in a moment. If you add these up, notice how this number would have to add down here to 50. So you can kind of, I hate that it zooms back out when I do that. But since this is 50 right here, these numbers have to add up. And since this is 20, this number has to add up. So this would have to be 13.3. And you see this is 50 right here, and this is 20. And everything has to add up to 70. You can check your work by moving one over, as in you would just simply take right here and say, what if we want to do the expected cell count for the one on the top right? And it'd be row total times column total over grand total, and we can check our work. And so with the work, I think I do have one math error. I feel like there's one math error in this because everything's not adding up. 20 times 50 divided by 70, and that's 14.3. So this one I think is the math error right there, 14.3. Yeah, that is the math error. Brian can't math. And something, or that's going to be 5.7. That's why that one's also wrong. That's what happened. It was that I did this one wrong. That's why you should always check your math. And we can double check that one. That one's 20 times 20 over 70. Is this making sense right here? This is not bad practice to do. Make sure you math correctly. 20 times 20 over 70, which is 400 over 70. And there it is right there, 5.7. So these are all the expected counts. Now, after you get the expected counts, what you would expect to see, so everything right here is an expected count. So let's just highlight this as this. These are all the expecteds we found. Now you need to find these cell chi-squareds, which means you need to make another matrix. If you're doing this all by hand, it takes a while. And within this matrix, do all the observed minus expected squared or expected. So you would take all the observed of like 40 minus 35.7, and then do quantity squared over 35.7, and that's going to equal that cell chi-squared. And then you would do 10 minus 14.3 quantity squared over, and you get it right here. We'd have to do all of it. This is going to equal to certain values. When you solve this all out, we're going to do a hypothetical. I'm going to write hypothetical above this. So let me write hypothetical, like made up. I just want to get to the next topic. If this was like 4, and this was 3, and this was 2, and this was 3, you would then sum these up to get the Pearson chi-squared. Who follows me on this, that the step now is to take all these cell chi-squareds and sum them up. As it says right there, you sum up all the cell chi-squareds. So this would be a total of equal to 12. And with 12 being the chi-squared, you then take and plot that on the proper degrees of freedom chi-squared. So this is a 2 by 2 because there's 2 answers to each question. Burgers, yes, no. And did you pass? Yes, no. That's 2 by 2, meaning it has 1 times 1 degrees of freedom equal to 1 df. So the degrees of freedom is equal to 1. We then take and plot and go to the right of it. So we then take whatever we find. This is going to be a very small p-value. And it leads to rejecting or failing to reject the null. But this has been the full formula sheet explaining what these values are, what they mean, 1 degree of freedom, find the p-value. You do not have to do this on the test. P-value here would be very small, but you should understand the theory of how to do this, and we would reject the null right here. The p-value is well below the 0.05 standard, so usually we use 0.05 alpha unless otherwise stated. We would reject the null and have evidence to the alternative. What topic should we do next? Let's take a quick break. Woo! Oh my gosh, what is going on? Just the world's going crazy. Got Evil Brian on the screen. Oh my gosh. How's everyone doing? Take a quick break right here. What topic should we do next? That was the full reject the null because there is evidence to the alternative. It looks like they are associated. Eating a burger makes you more likely to pass the test. Wesley, good to see you there. Man, let's see if there's any emails. I got to get my lunch today, too. I think. Oh, there's a celebration day. I think there's a celebration. Let's see. Celebration. 3 to 5. I think there's ice cream and stuff. This is 5 tickets to Dollywood. Oh, I should totally. I'll feel bad if I win that, though, because it's like graduate students. They need some Dollywood tickets. They need the Dollywood tickets. I can go to Dollywood. The graduate students, especially if they're not from Knoxville, then they need to go check out Dollywood. 3 to 5 seniors? Wait, oh, no. Oh, it's for GSA, graduate students. Maybe I misspoke. Graduate students. No, it's graduate students. Don't. And then there's the ramen Rachel's doing. And I sent out. Did I send out 207? I don't think I sent out. Let me send out another announcement because I didn't send it to 207 yet. Let me say currently reviewing. What topic should we do next, Zariah? What topic should we do next? You name it, we do it. We cover it. We'll review it. 20, 25 minutes on it. Depending on how long it is. Maybe it'll be quicker. And we'll do 2 topics during that time frame. Pick the topic, whatever you want. Kahoot at 4 p.m. Currently reviewing live. No sleep till the... No! Get some sleep. That's why we're doing it during the day right here, Derek. Get some good sleep. Always treat yourself well. Good sleep, good food, good interaction with family and friends, good exercise. All those things are very important. And I truly mean that. If you start to get too out of whack on everything, then things get in disarray. Like if you don't get enough exercise. I found it out. I was sitting around for too long each day and my body got sore. Like you get sore, your body's like, oh, you don't want to move? Sure. Then we will Solving for power. We got chapter 13 and 14, solving for power. We'll never actually solve for power, but we talk about power. So let's do confidence intervals for the mean and the proportion, and then we'll maybe talk something right here. Confidence intervals for means and proportions, and then let's talk about errors and power. That'll probably be a shorter section, but we'll talk about that next. Okay. Break is finishing up. We take a little break between each section. And please drop any questions and just follow along. So now we'll do chapter 13/14 so people know. Okay, let's go check it out here on the main screen. So we're talking about confidence intervals for the mean and the proportion. It helps to know the formulas. And let's talk about here. We just have to understand it. Pretty much, Soraya, pretty much. And so with this, here's 2 of the confidence intervals out of the 3 you have to know for the test. You know what? Let's just write all 3. So the first interval we learn is this. Now, what is this interval trying to estimate? I said it right then for a reason. This interval is trying to estimate what? This interval right here is trying to estimate what? What is that interval trying to estimate? Well, the first part of the interval always kind of clues you in on it. So what is the interval trying to estimate? Does anyone know? Well, we're making an interval from the sample proportion. So the interval's probably trying to estimate what? We made an interval from the sample proportion, the true proportion. So it's trying to estimate. So the truth we want to understand is this. And the estimate of the truth is this. This is where the margin of error begins. This is the confidence level, and this is the standard error. I wish I could move that. I might be able to move it a little more down. Can't do it. So the standard error is this last component. That is the standard error. So notice how we have the truth we're trying to estimate, the estimate of the truth, The margin of error begins right here. Everything after the plus or minus is a margin of error. The confidence level is related to the z we pick based on how confident we are, and the standard error is the last component, measuring an amount of variation in the estimate we have of the truth. Next, we did an interval of y bar. So what are we trying to estimate, or are we trying to understand? The truth we're trying to understand. This right here, Firebird, good question. And we can do that during the next break. I'll show you some videos. But this video right here is going to be segmented with each part, and we're just going through doing each concept. We're trying to estimate the true mean, which is mu. We're trying to estimate the true mean, which is mu. And so it's y bar. So since we're doing t, Mr. T's mean, if you're doing drugs, and s over square root of n. Zachariah, good to see you there. So that's the standard error. Next, we have y bar 1 minus y bar 2. I'm going to make it a little bit smaller, right? Never change the aspect ratio until you change it. Plus or minus t star with a complicated degrees of freedom formula, which we'll never have you solve for. And then s1 squared over n1 plus s2 squared over n2 square root. And we're trying to estimate the true difference in the means. We're trying to estimate the true difference in the means. And just try to look at the formulas. The truth is always some population parameter, the true proportion, the true mean, the true difference in the means. What we estimate the truth to be, I guess we could do a similar color, is based on the sample proportion, the sample mean, the sample difference between the two means. Next, the margin of error is always the plus or minus beginning it. Just to make it clear, the margin of error encompasses everything beyond there. So everything beyond this is in the margin of error. The margin of error isn't the plus or minus by itself. It is everything beyond it. When you say plus or minus 3, that's the margin of error on the estimate. So this begins the statement of the margin of error. The estimate is the center of the interval, the best guess of it. And so when you draw out your intervals visually speaking, your intervals are going to look like the following. The margin of error is one number when you solve for it, true. When you solve for it, you're like 10 plus or minus 3, and that'd be the margin of error. When you do it mathematically, it does have a level of confidence, and it does also have a standard error in it. But you always, and the interval is a lower and higher true. Great job, Zariah. Because when you look right here, what you get is an interval looks like this, and the margin of error is this. The margin of error is what the length of the interval. If you talk about the length of the interval, how long the interval is from the upper to the lower, so this is the lower, and this is the upper, the margin of error is what the length of the interval. So that's the lower to the upper. It's half the length. And you can do the margin of error really quickly. If I were to tell you an interval goes from, let's say, 30 to 50, what would be the margin of error? If an interval goes from 30 to 50, what would be the margin of error? So an interval goes from 30 to 50. What is the margin of error? And it works if you can just say it. Great job right there, everyone getting it. 40 is the center plus or minus 10. Does that make sense right there? So you can see the numbers we've highlighted. 40 would be the center of the interval, and then the margin of error is plus or minus 10, leading to the upper bound and the lower bound of the interval. Now, when you think about this margin of error, there's two main things that control the margin of error. What are the two main things that control the margin of error? The two main things that control the margin of error, and you could break it down different ways, but tell me the two things that really control the margin of error. What are two things that really control the margin of error? I'm going to do this to my interval. What are two things that really control the margin of error? Correct. Great job, Zariah. So the two things that really control the margin of error, as Zariah said perfectly right there, are going to be the sample size and how confident you are. And let's just take a look at this and bring in the graphic back on the screen right here. So, whoops. Was it going to do that? Here, let's do this. Because I want to do some fancy stuff with it. There we go. Wrong thing. There we go. So when you have your confidence interval, if you were to take a larger sample size, look at where the sample size is at, what happens to the standard error when sample size gets larger? Who can explain what happens to the standard error as sample size gets larger? As samples, look at your dividing by it. So as sample size gets larger, standard error gets water. As sample size gets larger, the standard error gets water because you're dividing by it. So just plug in some numbers. Pretend we go from a sample size of, let's say, such a big pen right there. Let's say we go from 10 to 1,000. Well, you're dividing by bigger numbers because it's in the denominator. So the standard error gets smaller. So if the standard error gets smaller, then the whole margin of error gets smaller because it's smaller values. So does it logically make sense that when you take a bigger sample, your margin of error gets smaller? Did everyone hear that? When you take a bigger sample, it decreases the standard error, which makes the component of the margin of error smaller. And then we'll talk about Z here next, and we'll talk about calculating those too. But a key note, and good questions, Derek, is that when you take larger samples, the big thing to know is that it decreases the margin of error, and it decreases it by making the standard error smaller. No matter what equation you're doing, larger samples equate to smaller standard errors, and when you have a larger sample, smaller standard error, it means smaller and smaller margin of error. Now, the second component, which Derek is bringing up right here, is going to be the amount of confidence we have. And the amount of confidence we have is related to the Z star we pick, or T star. So that star right there literally means based on a confidence. So when you make your interval, you pick how much of the curve to shade. So you could pick something like 68. Now, about what would the Z-score be if you pick 68? About, not perfectly, but very close, and we memorize this. I'll answer a few more questions. But if we make a 68% confidence interval, the Z-score is about what? A 68% confidence interval has a Z-score of about, not perfectly, but about what? 68% confidence has a Z-score of about what? 68 is about 1. And that's that classic 68, 95, 99.7. So think about this. If you know 68 is 1, 95 is 2, and 99.7 is 3, a Z-score for a 98% confidence interval would be logically between 1 and 1. Think about a Z-score for a 98% confidence interval. Where would it be? 68, 95, 99.7. 68%, 95 covered, 99.7. It'd be between a Z-score of what and what? Would it be between 1 and 2, 68, 95? Would it be between 2 and 3? It would be, because this is 95 and 99.7. So that's what we're doing on our applets right here. The applets are just a way for us to find the answers. So when we go, and I hope this answers Derek right there. I'm confused on finding the Z and the T. I don't know how to calculate those. We won't have you do the applets on the test, but we do want you to understand conceptually that when you are covering a certain amount of the curve, that's what you're saying when you're saying I am 99.7% confident. So we're going to go right here and see the apps in a second. Should we just remember that the confidence intervals are related to the Z-score or the T by which they're created? Pretty much. That's like a key learning objective. And the confidence interval is the between. So when we do a confidence interval, we do between, and we're going to enter in how confident we are. And take a look. When you start right here, it's 68. If we do to 2 decimals, I think we're at 2 decimals, 68 is basically 1. 68. 95. Oops, I broke the app. 99.7. 68. 95. We got to go to between again. There we go. 99.73. And it's because the 68, 95, 99.7 are numbers we memorize. There's more exact numbers. 95 is actually 1.96 or 1.95996 if you carry more decimals. No one actually carries it as many decimals as I do. That's a 4. And I think there's a 6 right after that. No, there's not. I was wrong. But usually people just do to about 3 decimals when they do this. And so things like an 80% would be 1.282 when you round to that. And 90%, because think you're going 68. So you have to go further out to get to an 80%. You're not going quite to 95 when you go to a 90. So 90 can't be as big as 2 or 1.96. 90 is 1.645. These are classic numbers a lot of statisticians know. Or 98% would be further than a 95. Does this make sense, Derek? Like talking about how this z-score is found. Usually statisticians either memorize them or use tables or look them up. We want you to know the theory of how it comes from, the amount of area shaded in the middle part of the curve. So you can remember with chapter 5, 68, 95, 99.7. So the more confident you are, the wider the interval gets. And the more confident you are, the less what the interval is. We're practicing this a lot. You don't need to memorize them. We would give them to you on the test. So the more confident you are, the what the interval is. Because when you go from a 68, 95, 9.7, the interval's getting more confident. The margin of error is getting bigger. And I guess I can't make both things do it together, but it'd be like, this would be a 99.7% confidence interval. It would extend like out. I got that. So it would extend like this. That'd be the 99.7. It gets less precise. And if you only make a 95% confidence interval, it would go from here to here, covering the middle 95. If you make a 68% confidence interval, the lower to the upper goes in. The center is still in the same spot. Does that make sense visually, what I'm showing you right here? Like when you get more confident, whoops, now I'm racing backwards. So a 68% confidence interval only covers the middle 68% of the curve. And we would use the applet to find these answers right here of like, what is the z-score for a 90% confidence interval, 1.645. Now, the z never changes because the z does not have with it what? So who can answer my question here? The z is always the same, and I'm going to answer Derek's question. The z never changes, so I know 68 is 1.6. 68 is basically 1. 90 is 1.645. The z never changes because the z does not have with it what? The z is one distribution, not a family of distributions. It never changes because the z does not have what's. So to have the smallest margin of error, you have less confidence. Yes, but you don't usually want to do less confidence because that sacrifices, like imagine I am 1% confident. You'd have a very small margin of error. And they'd be like, well, that's not a really good, your confidence is too low. So yeah. So the z does not have what? Think about the difference between the z and the t. The difference between the z and the t, Derek got it right there, the z does not have degrees of freedom. Degrees of freedom tell you the shape of the distribution you're working with. And you can see it right here, z does not have a degrees of freedom subscript. So the subscript on the degrees of freedom tell you how to find it, n-1 for the one sample t, two sample t is too complicated. And so now we go here to the t applet, and you can see how the t looks. I actually have a more favorite applet. Is that the right word? I don't know. Statdistributions.com really shows, because I love Adam's applet. It's great. But when you go to this t right here, I want you to look at the t with 1 degree of freedom. The t with 1 degree of freedom is really smashed down. I like to say Mr. T smashes it down. And as he gives it more freedom, it rises up into the normal. Now, the reason this applet looks like this and the other one doesn't is this has a static scale. So you're actually missing a lot of the ends of the curve right here. Notice that it goes further out, and then the t turns more into the normal with higher degrees of freedom. Adam's applet perfectly does it the same, but it changes the scale. If you zoom into 3 and -3, you will see the same picture right here as you see with the t with 1 degree of freedom. So there's with 1 degree of freedom on this applet, and over here the same visualization. As you increase the degrees of freedom, notice how it changed it, it turns into the normal, and you can see what is the normal. So why do we use the t? Very quickly on this. William Gossett, while working at Guinness Beer, found out that the t was not perfectly describing the normal curve. The normal curve wasn't perfect for what he was doing. It had error in it, and it was related to his sample size. So at smaller samples, he had larger errors. So he created a paper called On the Probable Error of the Mean, published it in Biometrica in, I think, 1905. And this paper was revolutionary, but he used a pseudonym. He called it Student's T. Student was the one who published it. So that's why it's called the Student's T distribution. Why do you call it T? Maybe it's because Gossett, his last name ends with T. But he used the pseudonym of Student, so it's Student's T, and so that's why it's the T distribution. William Gossett at Guinness Beer created this distribution in around 1905. Biometrica was the journal. Still exists today, and very hard journal to publish in. And there's a story that apparently him and Ronald Fisher, another famous statistician, Crack me up, Derek, right there. There's a story that another famous statistician and him were beefing, and they that's why he used a pseudonym, because they're like, he's not going to publish his work. Does the Z star say based on confidence level? But you said the Z star is based on confidence level. True. So when you're doing the Z star, if you're doing like a 95% confidence, it's 1.96. And then if you're doing 98, it's 2.3263. So the Z and the T star are both based on how confident you are. So a problem would have to read something like build a 98% confidence interval and for the mean, and your sample size is 10. So go ahead and grab me the T star when we're trying to build a 95% confidence interval for the mean and your sample size is 10. So if you look at what you're doing right here, you're building a 95% confidence interval for the mean and your sample size is 10, or it said 98%. 98% confidence interval for the mean and your sample size is 10, which means you're using this interval right here. 98% confidence interval for the mean and your sample size is 10. I put the T up there for a reason. So this is the interval you'd use. You're building a 98% confidence interval for the mean and your sample size is 10. You're not finding... So your sample size is 10. So what are the degrees of freedom? So anytime you get sample size and you're doing the mean, you have to find degrees of freedom. So degrees of freedom are what? Well, your sample size is 10, right? So since sample size is 10, boom, you got it, Derek. Degrees of freedom are 9. So now you go to the applet and you enter in degrees of freedom 9. You make sure you're on the T applet, not the normal. You bought dropping some degrees of freedom. 9 degrees of freedom, and then I think we said 98% confident and do between, and there would be the value. So there is a 98% confidence interval with 9 degrees of freedom. Does that make sense? Does you want me? I can do another one if you want. So this would be, and you wouldn't do this on the test. Yeah, if you put 95, then you'll get the 95% confident. Yeah, I might have said 95 also. And you see if you become more confident, the value gets bigger, the interval gets wider. So don't worry if you put 95. And we wouldn't have you use the applet on the test, but understand the theory that more confident means wider interval. Wider interval means less precise. And the T has with it degrees of freedom, created by William Gossett at Guinness Beer. So it's a lot of those key things I'm mentioning right here that I'm saying multiple times. So it's not T correct, Derek. That is correct. These things right here are subscript, and really good questions, Derek. We're bringing back the sheet right here. Those things down below it are subscripts, and the subscripts are not multiply. You do not multiply by these. There's no subscript on and same with the chi-squared. It's a subscript for telling you the shape of the distribution you're working with or the certain distribution from the family. Do not multiply by it. I see that, yeah, that's what happened right there in the previous one. Don't multiply by it. It's a subscript. Okay, let me see right here. How are we doing? What is a subscript? Yeah. A subscript means like, so another way we see subscripts right here is we see it with like the null, and the subscript is down there. Superscript is when you see something like chi-squared. That is a superscript. So subscript, like below, sub, and super, I guess, means above. I don't know Latin, that super. But mathematical idea of just it's script. It's meant to be words, not meant to be math. So superscript, subscript, chi-squared, I guess you're multiplying by, but the superscript right there means multiply. So good thing. And Word actually has these. You can go right here to home, and you can see the subscript and superscript. If you hover over this, subscript right there, and superscript right there. Good. Thank you, Dare, for asking. I wouldn't have known those words. I think I only learned it when I was teaching. You kind of know it in the background. You're like, wait, what's a subscript or what's a superscript? You don't hear it too often. You hear like multiplier, square, or caret, or things like that. So, yeah. And, well, we try to spend 20 to 30 minutes, I'd say, on each topic. Any last questions about confidence intervals? So this was confidence intervals for the mean and the proportion. And you can see these all right here. They have very similar components. The confidence level is based on the Z or the T. And you can see what we're estimating. And then you can also see the degrees of freedom. Do a nice light purple. Degrees of freedom right there. Let's do an example question to end. Okay. So let's say, here's an example question to end. Brian wants to figure out if students really do love Taco Bell. They had Taco Bell yesterday. I should have got some. He asks 200 students if they like it, and 150 say they do. Build a 95% confidence interval to estimate the true proportion of students who love Taco Bell. Okay, so the first thing, we always say it, is identify your what first with any question. We could do hypothesis testing next. First things first, identify what. Oh, no, we need to do errors in power next. First things first, it's always about that what. You know it, you
Notation,
love it.
brother.
You got to find this to be able to solve it. Great job, Drew, right there. You got to be able to do what here? What do you need to do? What do you need to solve for whenever you get problems? Very important to know this. We started off the review with this. What do you want to get? It's all about that notation, brother. Notation, brother. That's what Leo would say. So we've got right here, what are these things in notation? Tell me these things I'm highlighting. I'll highlight them here for you. So what are these things in notation, and what can we get from them? So try to tell me what these are. I'll write the formula for you. So the formula is p hat. Because remember, we're trying to solve for p, which is the true proportion. So we're trying to estimate the true proportion. That's what we want to understand. We don't know that. And careful. Good work. But be careful. Let's take it. We'll check some stuff right here. Derek, excellent work. Sorry, excellent work. But we'll wait. Let's think. Okay, so wait, you ready, Derek? Really good questions. Are you ready? We bought dropping some hats in the chat. P hat and Q hat can only be between what and what? P hat and Q hat can only be between what and what values? When thought of as a proportion, P hat and Q hat can only be between what and what values? 0 and 1. At least great work right there. So they can only be between 0 and 1. Because it's proportion. Or if we say a percent, it could be a percent, like 30% or something, but that means 0.30. So we're close. And don't worry, a lot of people get this one wrong. This is like a good question to do because a lot of people like forget a certain value that we talk about. So what are these values right here? So it says he asks 200 students. So what does that mean? He asks 200 students. So what is that? I think we can get this one. Let's do that one first. He asks 200 students. We'll do different colors right here to associate it with it. He asks 200. Nice job, Derek. Yep, Derek's getting it. He asks 200 students. So if I ask 200 students, the 200 students I ask is n. So now I think Derek figured it out. What is 150? This is where people get stuck because it's not even on the formula sheet. What is 150? This is where sometimes I think we outthink ourselves. And Zariah, excellent work. I've stopped giving points if you haven't noticed because I don't want to because the points are kind of over. And make sure you check your points. But that's technically giving you a little more, but not those 100,000 bursts we used to get. So this right here is x, and p hat is x over n. Today, the points is learning. Exactly, maxed out on points. And so p hat, and great job right here, is 150 over 200. And once we get p hat, how do we find q hat? You know it. You love it. Q hat is 1 minus p hat equals to 1 minus 0.75 equals to 0.25. Make sure to add p hat and q hat, and they add up to 1. That's the way you know you found them right there. So p hat and q hat add up to 1. That's a good check. So p hat is this, and q hat is this, 0.25. They add up to 1. And so we know what p hat is. And then how do we get z? What's the deal? What's the deal with z? How do we get z? How do we get z? How do we get z? Now remember, z is related to something. Z is related to how what we are. Z is related to how what we are. It is 1.96 because it's related to how confident we are. So the 95% right there means shade the middle 95% of the curve. So the z-score is going to be 1.96 because that is where the middle 95% of the curve is shaded. So it's related to, the star means related to the confidence, And the z is going to be given to you on the test. We don't usually have you solve for a z unless we are doing a test. Do want to make that clear. On the test, we've mentioned this a lot right here. When you do a statistical test, the z is the standardized difference. When you do a confidence interval, it has a star for a reason. The star means picked on how confident you are. So when you solve for this interval right here, we're just going to plug the numbers in. We are doing the center of 0.75 plus or minus 1.96. We've entered into the margin of error right now. And now we will do square root 0.75 times 0.25. And then we are going to do divide by 200. 752. I shouldn't have done those numbers. My handwriting is so bad. And so the standard error, I always solve the standard error first and then divide by 200 square root. And so that's the standard error, which we're going to call that 3%. You know what's so beautiful about this? Nice job. Is that I think you have the margin of error, Derek. Good work, Derek. I think you have no, you're good. You're doing great. This is the standard error. So remember our components and excellent work. Derek, I wish I gave you some points, Derek. You're doing great. I have people get over 100 in this class. You'd be shocked at the amount of things they get wrong in the chat. I say get it wrong in class, get it right on the test. The only way you know what you know or don't know what you know is to practice. Then you get it down, you get those mistakes out of the way, and you ace the test. Derek, good work right there, and I mean that. So this is the standard error, and this is the confidence level, and that's going to basically times 2 it because there was some decimal change we didn't do, and then plus or minus 0.75. So what's the interval? The interval is going to be 75% plus or minus 6%. So that is going to equal a lower bound of 0.69 to 0.81. So how do we interpret this interval? I am 95% confident that the true proportion of students who love Taco Bell is contained in the interval 69% to 81%. So Mebot's about to drop that interpretation right there. I am 95% confident the true proportion of students who love Taco Bell is contained in the interval 69% to 81%. And that's how we interpret intervals. Mebot, come on. Oh, I got to write confidence for confidence interval. Okay, should we do statistical? Let's take a quick break. Oh, no, we got to do errors and powers. This is really good. Doing like 30-minute sections. Oh, wait, we don't want to put the next thing in here yet. Let's go back. Woo! I got to grab my lunch. I am 95% confident the true proportion of students who love Taco Bell is contained in the interval 69% to 81%. I got to get Taco Bell sponsorship. I think the Taco Bell on the strip has some sort of like area above that I don't even know if they're using. I want to do a paper like I lived in a Taco Bell for a week. When I was a kid, it was my dream to live in a Taco Bell. And I wonder if I could do office hours. Oh, no worries, right? It'll be recorded so you can check it out later. I wonder if I could do my office hours in Taco. Do you think if I contact Taco Bell and I say, hey, look, I want to have like, I lived in Taco Bell for a week. I could just do office hours a few days there. Like 3 to 5 office hours. I don't even need to sleep there. Sleep in Taco Bell. I slept at Taco Bell. I lived in Taco Bell. You don't love Taco Bell? Derek, no. Come on. They got cheesy, beefy gordita crunch. They got the Fiesta potato bowl. They got Mexican pizza, which is probably not quite like a Mexican pizza. It's just some things they threw together and called it a Mexican pizza. But still pretty good. Big Dos Bros fan here. Dos Bros. I gotta check out Dos Bros then. We love Soccer Taco even more. If you told me Soccer Taco or Taco Bell, I'm going Soccer Taco. It's really good, really good. If you haven't been to the Market Square one's my favorite. We used to, I think her name was Jessica. Yeah, she was like the best waitress. Margaritas there. My wife and I used to live downtown, and you could just, I mean, always personal opinion. I'm not gonna say it's personal opinion. Do this. Always have a DD, designated driver. Never get too inebriated if you're going out to restaurants either. But always have a way to get back home that does not involve you endangering yourself or the lives of others. Just being real right there. And so when we lived downtown, it was nice that we could just walk down to Soccer Taco, have a pitcher of margaritas, and, walk back. I mean, I'm almost 200 pounds, so pitcher of margaritas. I can't do it by myself, but take the little bit off that I'm swimming with my wife. So then this is good. Zool's pretty good. Zool, I've had a few Zool. Do they have the peanut butter beer, Derek? I've heard, is that Zool with the peanut butter? I've heard it sells out like that. I've heard it just like I've heard Zool has a few things. I've heard literally there's like a line around the block. Everyone's like, dude, Zool. So shout out to Zool right there. Good brewery downtown. Heard a lot of great things. I've had some Zool. Maybe I should pick some up for my wife. She's more of a beer drinker than I am. I'm more like rum. And I don't even drink that much these days. I just can't. Just ask anyone who's in their 40s, 50s, 60s, whatever, and be like, oh man, you want to go drink? They'll be like, no. Like I'll have a rum and Coke on a Friday night. I'll have like a margarita these days, but my days of my 2 or 3 Four Locos, is it 1 Four Loco? Woo! 2 Four Locos? Ho-ho! 3, you're crazy. Because the four Four Locos is 4, you're crazy. No one does. I'm being actually serious. Don't do that. A glass of wine. I'll have a glass of, I like sweet wines like Rieslings. A Riesling's really good. Maybe that's lame. A late harvest Vignal. Something like that. Like an ice wine, dessert wine, things like that. Which is, I don't know. And then it's really sweet. It's very syrupy. But I mean, like you get a sweet wine with a cheesecake or something. It's good stuff. Good stuff. Okay, I could do like a Merlot with like a good dry Merlot with a steak. It's just, used to do that a lot. Not a lot, but you know, like if I got a good steak, you can get a good glass of wine for like $10. Used to be 6, 7. Let's hop back in and talk about statistical power and errors and memorize these ideas, Derek. Oh man. Now I want a good steak. You can't do it to me. Have you had any good convos on Ped recently? Yeah, actually I have. Really good convos yesterday. We'll talk about this, then we'll get back because this is our little break right here. But I mean this. It is more fun to me to talk to people I disagree with than agree with. I love talking to people I agree with. My wife and I actually, she'll disagree with me on purpose to have some fun because she knows I like kind of testing my ideas. And I think, personally, I think you need to be able to debate your ideas both civilly and with good facts. And you only really know that your ideas can stand the test if you go out there and say your ideas and get the pushback. And that's one of the best ways, and do it civilly and respectfully. And it's tough though, because there's a lot of ideas that are very, can raise the heat. But I had some good conversations yesterday. I had some very respectful, civil conversations, and had some disagreements, had some agreements. Because there's even people you disagree with. This is my last thought, and then we're going to do the next section. Anyone you talk to, and that's the issue, right? That is the issue. And I'll say this. There was a conversation about a year ago that I was involved with, and people started to get angry, and I just walked away. Like, it started to get to where I was like, this isn't what I want to be around. So I just walked away mid-conversation because and it wasn't, I didn't say anything. I just want to make that clear. It was 2 people talking who I was around. They were engaging, and they started to get a little heated with each other. And it wasn't in any way, it just didn't become a conversation that I thought was in the right place. Does that make sense? So if I had said something, I'd been like, you can have your conversation. It's not how I wish to discuss things. I think when you have conversations with people, you have to actively listen. You have to respond to what they say. It has to be in good faith. Like, you actually have to take what they're saying at its face value. And that can be tough. And I do think there are people, and I hate to say this, I think there's some people who will try to make it so you can't have a good conversation. I don't prefer to talk to those people. If someone is purposely trying to inflame others, and I will say this, if someone's trying to do that, like, I'll talk to people who do that, but if they're trying to make other people mad, maybe I'll try to segue them over to another spot. If they're purposely trying to, I don't like that. I don't like people who try to, don't try to rage bait people. I don't like rage baiting, and I'm not going to talk dishonestly about my views or anything like that, but I don't think we should try to get other people mad. I think we should try to have honest conversations as I blur away. I think we should try to have honest conversations about our views, and then we should learn to discuss things civilly. Oh, make sure the exclamation's first right there, Meredith. I think that's a good skill to have both in your workplace, in your life, in your partnerships. Because the number one thing, thank you, Derek, right there, is my last thought. The number one reason, and ask anyone who's ever had roommates, the number one reasons relationships break down is often, or a part of it, is because people stop talking. Ask anyone who's had roommate troubles and say, how often do you talk to your roommate? And they'll be like, oh, we don't talk. We're not on talking terms. It's a big thing is people just stop talking to each other. Now, there's probably some genesis of it, some sort of like fight or thing happened, but then the talking stops and the rift grows. So the only way you stop the rift, I believe, is to keep the conversations open. So I'm very big about that, like be able to talk to others, have civil conversations, and do so respectfully. So I think that's what we try to teach. That's what I try to do. Anyways, that was personal opinions with Brian. So let's go back to learning about errors and power over here on the main screen. Let's do it. Okay, we're back learning now. Back learning. Thank you, Derek. That was a really good little break from stats. We're doing breaks between these, and then we're morbing in. Okay, we got errors and power right here. So what is an error? So error. Can anyone explain to me, like, what is an error when we do a test? Like, why would someone make an error? People have asked me that. Like, well, why would you make these? So what is an error? Why would you make an error? Error? No one's going to do that. What's an error in a statistical test? Really? Tries to help me out by uncapitalizing, but that was not helpful. What is an error in a statistical test? What is an error in a statistical test? Okay, so an error is when we make the wrong choice about rejecting or not rejecting the null. So this is the error of the test. Kind of. Well, kind of. But whatever we decide at the end was the wrong choice. Does that make sense? Like imagine you are trying to figure out if let's say we're looking at, is this year's test in statistics harder than last year's test? Now, the average of this year's test is, let's say, an 80. That'd be nice. 80's good. 80's good. And you hypothesize that it should be about equal to, so the null hypothesis is going to be, we could write the null even. The null would be that the true mean is equal to 82. So this is the hypothesized value. Now, if the test is harder, you're looking for evidence that the test is lower than 82. Does this make sense? You believe currently that the average would be about the same as the historic average. You are looking for evidence that the true mean is less than 82, which would mean it's harder than last year's test. So think about this. You go out and talk to 4 of your friends. Your 4 friends made an average of an 80. When you run this statistical test, like we could actually run it here real quick, your standard deviation is equal to, let's say, 4. So that would mean the variation within your friend's scores was 4. So we run the test right here. T with n minus 1 degrees of freedom is equal to y bar minus mu naught over, see if you can get this before I can, see if you can solve this out. So all you're doing is just solving this test right here, and I did it this way for a reason because it's going to go into the other topics. Your friends made an 80 on average, you subtract the hypothesized value, you divide by the standard error, which is 4 divided by the square root of 4, which is a beautiful number. It is 2, and we get 2 over 2, which leads to a t-statistic of 1. And so if you draw this out, you're going to get a t with 3 degrees of freedom, because remember, degrees of freedom is equal to n minus 1 right here, so it's going to be 4 minus 1 equals 3, and actually the t is truthfully going to look way more flattened down. And so when we go out here, if you were to put your marks, you landed right here at a t of 1, and so you landed here, and does that look like a tiny bit of the curve or a lot of the curve? The area below, because remember, this tells you which way to shade, since you're doing the less than alternative, you shade to the left. Does that look like a tiny bit of the curve or a larger portion of the curve? Does that look like a tiny bit of the curve or a larger portion of the curve? What are your thoughts? Does that look like a tiny bit? And we can go right here, find p-value, degrees of freedom 3. I might have drawn it wrong then, Zariah. There it is right there. So here's the actual drawing of it. Here we'll zoom in on it a little bit here. So you see, I didn't draw it so perfectly, so don't trust my drawing. I was going between 3 and -3. So this is the actual drawing and the actual p-value, and then we have my sketch of it. Well, what do you think, Zariah? Did I do all right? How would you rate my drawing? There's the actual, and there's my drawing of it. So there's the actual, and there's the drawing. So if we stretch it out, it might kind of look like it. I don't know. There we go. There's 7 out of 10. Thank you, Zariah. 7 out of 10. Okay, so I'll do better next time. So with this right here, the p-value, you notice, is basically 0.2. So what would you do with this test? Since your p-value is 0.2, what would you do with this test? Remember, your p-value, we're going to just call it 0.2. Your p-value is 0.20. You're going to what the null. You're going to what the null, exactly. Well, since this one is not tiny because it's not below the alpha of 0.05, alpha is when we reject the null, you're going to what the null right here. Your p-value of 0.20 leads to you whatting the null. So p-value high, let the null fly. Great job, Elise, right there. So you're going to let the null be. We say when the p-value is low, reject the null. When the p-value is high, just let it fly. Don't reject the null. So you're going to believe that the average could still be 82. Now, what is the only error you can make when you fail to reject the null? That was a hint. So these are our tricks right here we learned in our class, that when you fail to reject the null, that's an F, you can only make a what error? A type 2. And what does a type 2 error mean? The null was actually what? In a type 2 error, the null is actually what? In a type 2 error, the null is actually what? In a type 2 error, the null is actually what? False. So in actuality, the test did have a lower average. I know you saw it in your sample, but it wasn't low enough for you to conclude you have enough evidence to say it's lower than what we thought previously. So you did not find that the test was lower. You didn't have enough evidence. And why might you have not had enough evidence? We'll review type 1 and type 2 in a moment. But why do you think this test led to you not having enough evidence? Take a look at the question itself and how it was worded. Look at the notation. You probably failed to find evidence due to having a 1. So look at the question and what data you got. You'd say, well, you didn't find enough evidence due to your small sample size. And this leads into the idea of statistical power. So statistical power is going to be the ability to correctly reject the false null. So in other words, remember how in that last problem we were looking at, is there a difference between like the previous score and the new score? Well, if the null is false, then the scores are actually lower. So your ability to detect that difference, to reject the null, is how powerful your test is. And there are 3 things that control power. Drop them in the chat if you know them. The 3 things that control power are going to be your sample size, how many people you talk to. Like if you talk to more friends, you'd be better able to detect if the test was harder this year. If you only talk to 4 friends, that's not a lot of power, as in ability to find results. Reject the false null. You could also change your alpha level. And so we could cheat with this. Alpha is your significance level, and it also controls the type 1 error. Alpha is literally your type 1 error rate. So you could just change this. How could you reject the null? Tell me with this test, we lost it. Tell me with this test over here, what could you change alpha to reject the null? Now you're doing it at the cost of making way more type 1 errors. But what could you change alpha to reject the null now? So now you'd find results and say, I reject the null because my alpha is what? And the researcher gets to pick alpha. We usually pick 0.05. That's usually what we do, because if you increase it, you increase your type 1 error rate, your false positive when you reject the null, but the null is true, type 1. So if you just raise alpha to 0.50, Now 50% of the time you make type 1 errors, so you have a very high type 1 error rate, but you can reject the null because your p-value is lower than alpha, and now you'd be in danger of making a type 1 error. Finding out there is something, you're saying, I think there's a difference, I have evidence of it, but maybe you were wrong. The null is true, there is no difference. And the thing is, we don't know when we've made errors. Like, if we don't know the truth, we can't actually check to see what the errors were. I'll go try to find... Why is Word being weird? Well, darn it. Might close out my Word documents during the next break because it's not scrolling down on the screen. Oh, is it all the way up here? Well, I'll be. Okie dokie. Here, we'll redo it, and then we will not go back to that previous tab. So the three things that control power are going to be sample size, alpha level, controlling type 1 error, and also effect size. So in my example, what is the effect size with the test? Remember the test that we're doing? And that would be true Zerai also. 0.22 would also allow you to reject the null. So in that previous example, what is the effect size theoretically? The effect size is the difference between the null and the truth. And remember, the null is that the test has the same average as last year. So what is the effect size? Well, the effect size, think about what effect size says, is how hard the test really is. So imagine the test is way harder this year. Hopefully it's not. But if the test is way harder, that'd be easier to detect because students would get lower averages, because that's the true difference between the test being the same as it was last year or way harder. If the test is about the same but a tiny bit harder, little bits. If the test is just a little bit harder, then with that, it'd be much harder to detect. And the effect size is theoretical. I mean, we can think of it as a real thing, like how much harder is the test, but we don't know and we can't manipulate that unless we like make the test harder. Like we could try to make a bigger effect, like let's make the test way harder, and then we would see lower averages so we could observe the effect of the harder test. Does that make sense what an effect is? The effect is like, what is the difference between the test being the same and the truth of how hard it actually is? And if there's a very small difference, it's only a little bit harder, it'd be hard to detect that. We'd need a very large sample or more willing to reject the null. The best way to change the power, which if any of these go up, power goes up. The best way to increase power is to get a larger sample. You can't always do that due to the cost or the time of getting a larger sample, but the best way to increase power is to increase sample. So power is actually the complement of a type 2 error. So 1 minus beta, and beta is type 2 error. Very important moment right here. Are alpha and beta complements? Are alpha and beta complements? Is alpha the complement of beta? Like if you say alpha is 0.5, beta is 0.95. No. Alpha and beta are not complements. They're inversely related. That's why I have these arrows colored this way. Everything is inversely related to beta on this side. Larger sample size, smaller beta. Larger alpha, smaller beta. Type 1 error lower, or type 1 error higher, type 2 error lower. Effect size is bigger, smaller beta. And then beta is inversely related to power. So since beta is inversely related to power, power is positively correlated with sample size, effect size, and alpha. As in, if you have a larger sample, your test is more powerful. If there's a bigger effect, the test is more powerful. It's easier to detect the effect. If you have higher alpha, you exchange your type 1 error rate because you have more type 1 errors, more false positives, and you have a lower type 2 error rate, and then you have a more powerful test. One of my favorite examples with this is the zombie apocalypse example. I use this one a lot. So you have the null hypothesis right here being that someone is human, probably a good thing to assume. So human is the null, and then here we have here a zombie. So you want evidence somebody is a zombie. So if power is being able to reject a false null, why would it be a type? Well, power isn't a type 2. Power is the complement of a type 2. So 1 minus beta is equal to power, where beta is the type 2 error. So let's think about a powerful test right here. You ready? A powerful test would be defined as one that can find zombies. Does that make sense? Because the power of a test is the ability to correctly reject the false null. And when you think about that in context, rejecting the false null means somebody is not a human, they are a zombie. Does that make sense right there? So it's the ability to detect zombies. Like the definition of power is the ability to correctly reject the false null, but the power of the test right here is going to be, can you find zombies? So let's think about 3 ways the test could be more powerful. The 3 ways would be, we could have a bigger effect size, a bigger sample size, or a bigger alpha. So let's think about what would be an effect size if you have somebody, what would be an effect size? Like, what's the effect size of detecting a zombie? Do you know it, Zariah? I'll take a moment and I'll see if people can think about it. Think about, you're trying to detect zombies, and what would be the effect size of detecting? Bigger scar, exactly. Or like, imagine you have somebody who's like smiling and happy, and like they have just a small boop on their arm, and they're like, no, this is from where I fell down. And then you have someone running at you. You're in a zombie apocalypse. This only applies in zombie apocalypse. And they're running at you, foaming at the mouth. And so this person's running at you, foaming at the mouth, and just scars all over them. Does that make sense? So this is the effect size right here. Does that make sense? So a bigger effect size would be, could this person be a zombie? Could the person on the left right there, who only has the small little nick on their arm, there's like, oh, there's nothing. Look, there's nothing. So what kind of error would you possibly make with the person on the left? The only error people would hopefully logically make is a what? Think of it. Well, I believe they're human. I would hopefully, I mean, unless everyone's a zombie, but I'd probably believe the person on the left is a human. So the only error you'd probably make is what? Who can figure that mystery out? The only error with the person on the left is you might say that what? Well, if you say they're human and you've made an error, what error is that? Type 1 or type 2? Type 1 or 2 in the chat. Well, in a type 1 error, the null is true. So if you believe they're human and they're human, you haven't made an error. Does that make sense? So in a type 1 error, the null is true. It's a fact that they're human, but it's false. This person over here is the person you might have made a type 1 error on. Does that make? Don't worry, it's practice. It's a weird example too. So it's like think about what a type 1 error means. What does it mean in a type 1 error? Which you probably, I don't think that's going to be a type 1 error. But in a type 1 error, the null is true, but you reject it. This person just woke up from a bad dream and bumped the wall 1,000 times, and they're still groggy. Turns out they're not a zombie, but you rejected the null. Does that make sense? How this could have been a type 1 error? If you thought they're a zombie, but the null is true, think about a type 1 error. In a type 1 error, the null is true. They are a human, but we reject it and say we have evidence they're a zombie. Now, we might have made the right choice. They might have been a zombie, so it wouldn't be an error. The type 1 is a human, but I say he's a zombie. Well, yes, that is true right there. I was thinking type 2 next. Correct job right there. That is a type 1 error. In a type 2 error, the null is false, but we failed to reject it. So what does it mean to fail to reject the null? What do we conclude about the individual if we fail to reject the null? So we're talking about that person there. In a type 2 error, the null is false, and we fail to reject it. These are the 2 F's of the type 2. Notice when you say the type 2, you say the null is false, and we fail to reject it. We think he's human because we don't reject the null, but he's a zombie because the null is false. Does that make sense right there? Hopefully, in a type 2, the null is false, and we fail to reject it. So it's false that he's a human. Try saying that right there. And then we fail to reject it, so we still believe he's human. So we make an error. Come at you. So, and the next thing, think about the person who would have a more powerful test. The person who's been in the zombie apocalypse for 1 day or 1 decade. Who would have better tests? Who would have... Now, it's good to do type 1 and type 2 slowly because it's easy to just reverse. Who would have better tests? The person who's been in the zombie apocalypse 1 day or 1 decade? The decade, because they have a bigger sample, right? So if they have a bigger sample, they'd be better able to reject the false null. And does that make sense? The person who's been in the zombie apocalypse longer would have a better ability to detect zombies. The idea of power, the ability to find zombies, reject the false null. If the null is false, then they're a zombie, and the ability to do that correctly would be finding the zombies. But what could we do with alpha? Now, if you're really scared, you could put your alpha from 0.05 all the way up to 1. Now, this is a horrible idea because what are you going to be doing in your zombie apocalypse? If you set your alpha to 1, what does that mean? Raise it to the roof. So that means any p-value, any evidence you get, any evidence that is not perfectly someone acting human, they twitch like this and you're like, zombie. Because the higher the alpha level is, the more willing you are to reject the null, but you might make a lot of what's now. It is safer. It's a little... I don't know the ethics of it in a zombie apocalypse. It's not very ethical to have an alpha of 1 in a zombie apocalypse, at least if you're taking out zombies. Only in zombie apocalypse. We're very, very clear it is all zombie apocalypse language. But the alpha of 1 means you think anyone you have any evidence, doesn't matter how small it is, you are going to believe they are a zombie. Does that make sense? Anytime you have evidence, you reject the null. Your p-value is equal to 0.99, you reject the null and you make a ton of type 1 errors because alpha is your type 1 error rate. But you would never make a type 2 error. You'd never be tricked. This is like the person hoarded up in a house, like, and anyone who comes by, they're like, get away from my land. They're like, you're a zombie. And you're like, no, look, we're humans. You're like, you're the zombie because I can tell you're, I don't know. Zombie apocalypses are weird. Miss humans versus zombies. So these are the 3 things down here. The effect size, once again, like how the bigger difference between someone being a human to a zombie, the bigger the difference is, the bigger your power and ability to detect, less likely to make a type 2 error. The bigger your sample size, the smaller your type 2 error, and the higher your power, and the bigger the alpha, which you get to pick. I will say this, the number one thing for the researcher to change is sample size. You do not control effect size. You do control alpha, but that messes with type 1 error. So I think what we should do statistical tests next, right? So let me do statistical. I'm going to walk around real quick. I think Soraya and other people said they have class. Let me save this. I'm going to go on break right here for probably about 15 minutes. We'll be back. But thank you, everyone. Ryan, Elise right there, and Derek's been here. Let's go on a 15-minute break. Let me put the timer on the screen. I have to go get my lunch because I haven't even lunched. I had a small breakfast. Let's go 15 minutes. This is the Podomoro method. I'm even doing it right now. 15-minute break. Check out the video later if you're leaving. Bye for now. Bye, everybody. Hey, everybody. I thought I was going to a different screen. Let's talk about some statistical tests. Another topic for today. Okay. Statistical tests. And there we go on the time. So statistical tests. Well, let me put chapter 15 on this. Or what is this? Chapter 16. Statistical tests are used a lot. Used in chapter 15/17/19. The idea of a statistical test. Okay. So one thing I want to point out right here is the formula sheet, which we covered at the start, gives you a lot of these statistical tests. And you can see them right here where it says hypothesis testing. So a statistical test, we'll talk about what it is in a second, but you can see statistical test and what type it is. It's a test on the proportion. Statistical test right here, a test on the mean. Statistical test, a test on the difference between the means. And the hypothesis test right here of the test of the chi-square test of independence is also another statistical test found by the sum of the cell chi-squareds. That's each a cell chi-squared right there. So what the heck is a statistical test? Statistical test. Brian definition. Not Googling it. So my definition of a statistical test would be a way of looking at something in a sample versus a hypothesized value and understanding in context how large this difference is. We start with a null hypothesis, and we either reject it or fail to reject, not reject, for an alternative. So that's kind of the basics. There's a lot to talk about within what I wrote right here. But I want to point out that when you do a statistical test, it always concludes with a p-value. So a statistical test, at least a lot of the ones we do, will have p-values. At least hypothesis testing. Hypothesis testing is going to have a p-value. So statistical hypothesis tests are going to have p-values. And with this, they have a null and alternative hypothesis. So let's start with the things we should know right here. I do what is called the HACS method for doing statistical tests. The HACS method is HACS, which stands for hypothesis, annotate notation, check conditions, and solve and state. Solve and state the conclusion. So that's the HACS method right there that I do. And we'll show some of this here in a moment, but I think it's really good to start with the hypothesis of it. And when you do a hypothesis test, the null and alternative are often written the following way. You often write your null by saying the null states. That's what H sub O means. And then you give a population parameter. So the population parameter is some thing we want to know about the population, like the true mean, the true proportion, all those things. And then you set it equal to some hypothesized value. Now, the researcher gets to pick this. The question would state something like on the practice test, 75% of students recycle is believed to be true, or we're testing it. So the hypothesized value can be anything you want. It's any sort of value you come up with. This is the null, and the alternative is very similar. The alternative uses H sub A to say the alternative states that some population parameter is either less than, greater than, or not equal to some hypothesized value. Now, when you look at this right here, we're not going to use all of these. We're not going to use, I had a student write that one time. I was like, no. Don't write all of them. We're only going to write one of the three based on the researcher's question. So the alternative is based on whatever the researcher wants to investigate. Whether they're investigating has the value decreased, increased, or changed from what it historically was, or what we want to test against. So when we do a population parameter, the population parameter right here will be the same one down here. And there's a few that we pick from in this class. The ones we pick from in this class are going to be, I don't want solve and state on the screen, so I'm going to go down here. The ones we pick from in this class are going to be either P, mu, or mu1 minus mu2. And then the hypothesized value, so over here, the hypothesized value that is put here will be the same value here. The hypothesized value is either going to be P naught which stands for the hypothesized true proportion, mu naught, which stands for the hypothesized true mean. Just by adding the naught, it means hypothesized true, or 0, and that is technically delta naught. So technically this is delta naught, which is the difference between the means hypothesized to be true, but a lot of times delta naught is equal to 0. Good to see there, Colin. So we often hypothesize the true difference between the means to be 0. Now let's look at how to use this, because whatever you select over here in list 1 for this needs to be allocated over here, as in this is the first thing, the first, the second, the third, and the third. So when you write out a null hypothesis, you would write something like, we are trying to see if the true mean is equal to, let's say, an 80 on the test. Now that makes 80 equal to mu naught, the hypothesized true mean, mu naught, by virtue of it being mu that we are testing. Good to see you, Colin. Yeah. And feel free to ask any questions. We're talking about testing right now because we're using mu. That makes the value over there mu naught. Just that's the way it works. Whatever you plug in right here, we could do a different one. We could say we want to see if 75% of students recycle. Well, that means we were testing the true proportion to see if it's 75%. So since we're doing P, that means we are hypothesizing. Notice that's the first one on the list I wrote right there. And for the final example right here, we can see if there's a difference between the scores of, let's say, UT students and Florida students. So we're looking at the difference between UT and Florida students. Notice how I'm just plugging in for 1 and 2, UT versus Florida, MUT, love it. And then that means we're testing a difference of 0, which is technically the delta naught, but 0 is the hypothesized difference. Now, what's really great is if you want to see if the means are different, you just carry over everything you wrote. Notice how this is the first thing. You don't change it. It would be that the true difference between UT minus Florida's average is, if we're seeing if there is a difference, we would just select the does not equals alternative. So that's how you would write it right there. And just notice how it kind of flows, that you're always picking a population parameter, and then you are picking a hypothesized value. Whatever value you choose to test goes right there as what you hypothesize is true. And so it depends on if you're hypothesizing a proportion, hypothesizing a mean, or hypothesizing the difference between two means is 0. If you pick P, this value is called P naught, but it is a value, as in we believe 75% of students recycle. That makes P naught 75% because you either recycle or you don't. Some people point out, wait a minute, that's a number, but when you ask somebody, do you recycle, it's going to be yes or no, do you recycle? So recycling leads to count data, not quite chi-squared data, but it is the count of people who recycle, and we can find the proportion of people who recycle. There is one break in this when writing the null and alternative, and the only small difference right here is chapter 19. It breaks the mold that I use to show students the steps. Of course, there's always the exception to the rule. I mean, that's not a rule, right? But the alternative would be X, or the null would be X is independent of Y, and X is not independent of Y. You can also say associated. That's another way to say that they are not independent. So you could say they are associated with each other. Like one would be related to the other. Related is another word. Associated, relationship, X and Y have a relationship. And this is when we do the chi-square test of independence. It's really easy to write the null, because what you could have is somebody lives on or off campus, and let's say, do they go to the Y, the T-Rec, or Gold's Gym? Gold's Gym. So now you have the gym someone goes to is independent, that'd be the first, the null, of where they live. That would mean living on or off. You think, well, people who live on campus would probably go to the T-Rec more. That'd be logical. We might see that in the data. That would be the observed. I'm not here to talk about the chi-squared so much, but just the null and alternative right now. The null would be the gym somebody goes to is independent of where they live. Or you could say where someone lives is independent of the gym they go to. Either or, rock knows. It doesn't matter. Now, the alternative would be the gym someone goes to is associated with where they live, which you'll probably find evidence of. You'll probably say there's big differences here between where someone lives and the gym they go to. So once again, the null is always to put independent between them. The gym someone goes to is independent of where they live. And this is only for the chi-squared. I want to make that clear. The chi-squared is when you have two categorical variables. It is chapter 19. That is how you write the null and the alternative for the chi-squared. The other chapters are shown here in the previous example, where we list out all of this, and this is how you do the previous examples, where you have either the start of it where we tested a proportion, tested a mean, or tested the difference between two means. And that's how to write your null and alternatives. Okay. Annotate notation, I would say the biggest thing for this, I could go back through the formula sheet, but let's not do that right now. Knowing things like the sample mean, like if I say the sample mean, what is the sample mean in notation? It is y bar. If I say the sample standard deviation, what is that? That is S. Great job, William. Good to see you. Thank you, William. I'll throw out some points. Let me.
Congratulations, Mewbot says, thank you, William.
Why are you even saying thank you? What are you... William, I think I remember your name in the chat. I think I remember. I know that name. Great job, William. Good to see you. Talking about all the graduates this morning at the Provost Coffee and Conversation, really talking about UT brand, students going forward, being good representatives of the university, talking great about the university. I talk great about UT. I love it here. I've had a lot of different jobs in my life, and this is my number one favorite. It gives me a lot of fulfillment. Very happy to be part of UT. My hair gets real long. Not going to get to my shoulders again. Probably not. Anyways, we say the sample size. You say it is lowercase n. We don't really use population size much. That would be capital N. Sample proportion is p hat. The amount of successes in a sample, like 2 out of 5 people own dogs, that would be 2 out of 5, which would be x over n equals p hat. So you would just solve right here. P hat equals 2 over 5 equals 40% of people own dogs. Q hat is going to be the complement of that, is equal to 0.60. P naught might be you hypothesize that everyone owns a dog. That'd be crazy. And then the complement of that is that no one does not own a dog. It's kind of weird to say that, but the hypothesized true proportion. The hypothesized true mean would be mu naught. There's a lot of notation to know. I always suggest writing it down, reviewing it, try to come up with examples of it. Like a researcher believes that students spend $12 on Taco Bell on average. That would be this. It's not what they saw in the data. A researcher believes that the students spend on average $12. So that makes it a hypothesized true mean, not what the truth is. Because if students actually spend, which would be very hard to tell, if students actually spend $13, then that would make that the true mean of what students spend. What you'd likely get is in a sample of so many students, like in a sample of 100, you saw that students spent on average $13. Just notice the small change to words that you saw in a sample students spent $13 between for a fact that students spend $13 or you hypothesize that students spent $12. Very small change to words, or a researcher believes. It can say believes, hypothesize, wants to test. That's where a mu naught, and that would be for a mean, versus p naught would be the hypothesized proportion. The little naught right there is the key to it is hypothesized to be true according to the null hypothesis. The conditions, a really good thing to talk about the conditions right here. So let's do a little bit on our conditions, because we have a really great way of memorizing it. I might try to even turn this into a better picture right here. So now we're talking about conditions for a little bit longer out here. Try to do 25 minutes on each section. Let's make a table. So we need 4 tests, or four columns, and then we need 5 rows. 4 columns, 1, 2, 3, 5 rows. Great job right there with the points. Okay. So the 4 different tests that we learned were, and let's center this. Let me just NASA center. So we had proportion, mean, 2 sample means, and chi-squared test. Does that make sense? So we have these right here, the associated chapters. Really? The associated chapters are chapter number 17, chapter 19, chapter 15, and I think 15 also puts them together. The types of variables are going to be, let's do 2 different pen colors right here. So we have in this a categorical variable here, categorical, and there we go. A lot of people are confused by the 2 sample t-test, but you're comparing 2 means. So you have to have the mean of group 1. So the way it looks is you'd have down here a categorical variable with like no and yes. Let me zoom out a little bit. So you'd have no and yes, making that categorical. And then the y-axis is actually where the quantitative is, and that leads to side-by-side box plots. So you're comparing the means of the two groups. So that's why it's a categorical x, quantitative y. The one sample t simply uses right here like a box plot. And I guess you could do a vertical box plot too, vertical or horizontal, rock knows. It doesn't really matter. Because you could call it the y variable of interest. You're analyzing this. So there's only one y variable right there. There's no bivariate data. Same thing over here. This would be something like a bar chart, and the bar chart only has something like no and yes. So a bar chart could be used to analyze proportions. So it's just one categorical variable. And over here on the far side, we have a mosaic plot where it is two categorical variables. And so you can see the mosaic plot drawn below. So this would be something like no, yes, and then no, yes also. It doesn't have to be no, yes, but you can see the visualizations right here. Also the notes on what things are. When you're doing proportions, it's only one categorical variable. Sometimes called a one sample proportion z-test. You can just call it a proportion test. This is called sometimes the one sample t-test because you're only testing one group, i.e. one sample. Two sample t-test is different though. And we do what's called the independent test, where that'll be one of the assumptions down here at the bottom. And you have two groups right here on, this is what's called the two sample. I guess we'd highlight that. I'm losing my pen. The two sample literally means the idea of two samples is this. This is not two samples. These are the people who said no. These are the people who said yes. And then within the no's and the yes, you took the means now. You took the mean of the no group, the mean of the yes group. And then this is not really two sample. Well, there's ways to do it, but we're not doing it right there. But I hope that differentiates, because as I look, I'm like, well, why wouldn't this be two samples? This could be used to analyze what is the difference between the means of people who attended the review, yes, versus those who didn't attend the review. This could be what is the proportion of people who attended the review. This would be the overall grade of people who attended the review, like what was the average. We could test the mean of the average. This could be, did you attend the review and did you pass the class? So hopefully we'd see more people who attend the review, or attending the review is associated with passing the class, low p-value. And so now the first condition, we're going to combine these cells right here. Everyone loves the first condition. You know it, you love it. The first condition is random. I swear they took away my merge cells thing on here. It's always hard to find now. Give it a moment. Found my merge cells. Merge cells. I knew you could right click. How did that? I don't know. Random. So random means you randomly collect your data. And so as long as you're randomly collecting your data, you are good on the randomness condition. So we randomly collect our data. And if we do that, we have met the condition of randomly collect your data. The next condition is the 10% condition. And so the 10% condition says you need to sample 10% or sample less than 10% of the population. Sample less than 10% of the population. And we could get into, I'll just mention it briefly, because everyone always wonders, why is it sample less than 10% of the population? Well, the reason is the more of the population you sample, you actually would decrease your amount of uncertainty. I'm going to try to do this off the top of my head. The true formula for making a confidence interval would actually be p hat plus or minus z star p hat q hat over n square root times, I think it's, we can just put it right here, times, and then capital N minus n, and then capital N minus 1. Maybe I'm going to write, this is from memory. Been trying to memorize it lately. And if you think about this theoretically, what goes on with this equation? This is beyond the test, not on the test, but anyone who wants to know why is it the 10% condition? Well, when you start to sample a lot of your population, your N gets about as big as your capital N. And what's going to happen to this right here is you are going to get, actually, I think I reversed the numbers. I did reverse the numbers, darn it, because that doesn't make sense mathematically. It's going to be capital N minus N, and then capital N minus 1. If you only take one observation, then N equals 1, and these two things right here would be the same, which leads to this whole thing, because they're both the same, numerator and denominator are the same, that leads to square root of 1, which is 1, and the formula wouldn't change because you're multiplying by 1. But as n goes to larger and larger numbers right here, so as the sample size gets bigger and closer to the population size, well, now you're going to reach where the top of this gets towards 0. And if the top of this equation goes towards 0, well, 0 divided by anything is 0, because 0 divided by whatever the bottom number is, doesn't matter, is 0. So what's going to happen here? Well, you're timesing your margin of error by 0. So this corrected equation actually makes it that as you sample more and more, you have lower amounts of uncertainty. So why does the 10% condition exist? Well, if you've sampled less than 10% of the population, so if you do less than 10%, this correction is very small. So the correction by which you'd multiply by is very small. We could solve this real quick. Here we'll do sample size of 1,000 people, and we sample 900. Okay, so we're just going to plug the numbers in here. Don't worry, you would never do this on the test, but 1,000 minus 900 is, of course, right there. Did I do it right? My brain's just... Oh, wait. We sampled 900? What am I doing? No wonder it's going crazy. We don't want to sample more than 10%. We want to sample 90, which is not more than 10%. So notice how 90 is less than 10% of the population. There's 1,000 individuals we want to learn about, and we sample 90, which is less than 10% of the population size. So now we're going to do the calculations. So 1,000 minus 90 is that. Now we're going to divide this by 999. So we take this number here and divide by capital N minus 1. And now we get the following, and we square root it. So if you look at this right here, this is what we would correct our standard error by, which will change the interval. It will make the interval tighter, but it's not a lot. There's not a big difference between the way we do the calculations and the precise way. Now, you could do it the precise way for finite populations, but that's the finite population correction, so if you break the 10% rule, you need to do a correction for oversampling, which would decrease the margin of errors and the amount of uncertainty for intervals and things. It would decrease the standard error, which is a measure of uncertainty. So the 10% condition is easily stated as sample less than 10% of the population. And if you want to know the advanced parts of it, we do have corrections, but without correcting it, sample less than 10% of the population. So next, we get to the next third condition. There are no order to these, but I like to say them in order. This is success/failure. And success/failure means you need at least 10 successes, at least 10 failures. So for a problem where you need at least 10 successes, at least 10 failures, let's take a look at how it would theoretically look. Well, it's going to get mad at me, isn't it? Sure. The problem with at least 10 successes, at least 10 failures would say something like, Brian knows that the UT population has, let's say, 4,000 students. Is that how big we are these days? No, wait, 40,000. We're 40,000. What am I saying? 4,000? 40,000. He goes out and samples 300 students. Good to see you, Megan. So we've definitely passed the 10% condition because we sampled less than 10% of the UT population. Now, from my sample, Brian believes that half the students like Taco Bell. So that would make P naught equal to 0.50. So when you do the success failure condition, it's that N P naught, lowercase n P naught, is greater than or equal to 10. So just solving the math right here, you can easily see that we would have here 300 times 0.50 is equal to 150. And you have to do N Q naught, which is the complement of P naught, is greater than or equal to 10 also. It's the same math because Q naught is also 0.50. So that's also 150. And so it's both NP naught and NQ naught when doing a hypothesis test. If we're doing a proportion, we don't have a hypothesis. If we're doing an interval, if we're doing an interval, we don't have a hypothesized value. We have what is seen in the sample, so we'd have a P hat. And so now both NP hat and NQ hat have to be greater than or equal to 10. So you'd have what you saw in the sample when doing an interval. So that is, you have to have at least 10 successes in your sample, at least 10 successes in your failures in your sample when doing intervals. If you're doing a hypothesize, it has to be that you hypothesize that there's at least 10 successes and you hypothesize that there's at least 10 failures. Get the hiccups right there. So that is the third condition for the proportion test and interval. Next, we get to the third condition for the mean, and it is always nearly normal. And so the nearly normal condition, put it right here too, because this is a means. So whenever you hear means, a good trick, we like to think of our tricks right here. Think Mr. T. Always talk about Mr. T. And when you hear the means, it's always going to be the nearly normal. That's always the third condition for the means. That's just a quick way to remember that those are connected. And there's a lot of ways to test this. One of the biggest ways to test it is via large enough n. So that's kind of a big way. We'll talk just theoretically about this for a moment. So central limit theorem applet. One of the biggest ways to test it is large enough n. And the large enough n was the way we used to do things, but we don't know the shape of the parent population anymore. We can only guess it. Because if you only have, let's say, 2 observations, then how would you know that came from a normal? But if you have a pretty large sample, like let's say you have a sample of 25, well, the sample of 25 is going to look like this right here. Here's your sample of 25. And you might say my sample of 25 doesn't show extreme skew. So via the central limit theorem, a sample size of 25 is large enough such that the distribution of the mean will be nearly normal. When you do this chapter, you don't know the truth. In sampling distributions on test 2, you knew the truth. In this chapter, you'd only know your sample data. And they'd be like, well, my sample data is not really skewed. So if your sample size is very small, you wouldn't know the shape of the original data it came from because you don't know the population parameters, the truths of the populations. So that's why it's a little harder to use large enough n. You can't say the distribution is normal and I only have a sample size of 1. You don't know the distribution is normal. You only have your sample data. So ways we can also investigate normality. You can look at the normality of your data 3 different ways, or 4. Let me think here. I think it's 4. The 4 different ways to do it is to simply, 1, look at a histogram. So if you look at a histogram and it looks normal, that's good. If it's skewed too much, that's bad, unless you can pass the large enough n condition. Like you have enough data to say, well, it's skewed, but I have a sample size of 100, so we have a large enough sample size. The way 2 of doing it, these are just different ways of doing the nearly normal, is to make a normal probability plot. And that's where if it follows the line, it's good, versus if it bends around the line, it's bad. The more it bends around the line, the worse it is. Way number 3 is to do a goodness of fit test, where if it has a high p-value, we say it's normal, versus a low p-value, we say it's not normal. All of these things down here are associated with it not being normal or evidence against normality. All of the things on the left side are associated with it being more normal, like a high p-value on the goodness of fit test. And last but not least, the large enough n method right here is, so large enough n would be, and technically it's lowercase n, so large enough n is where you look at the shape of your data as best you can tell. You wouldn't know that. You would only know this right here, and you would say, well, my data, you'd collect your data, you'd talk to your people, you would say, well, it only looks to have a little left skew. You don't know it's normal. Only a little bit of left skew. So with a sample size of 25, my sample size is large enough such that the distribution of the mean will be nearly normal. So the more skewed your data is, the larger your sample needs to be to make the distribution of the mean, which is this down here, nearly normal. Your original data doesn't become normal. The distribution of the mean for larger sample sizes become more normal. And so that's the ways to check it. You would not check it, hints, with things like a bar chart, pie chart, because those are for categorical data. You'd have to use histograms, looking at them to see how skewed they are. You have to use like a normal probability plot to see if it follows the line or not, a goodness of fit test to see if the p-value is high or the p-value is low. And we don't go into too much detail on analyzing those. We just want you to know like the condition of nearly normal, which means the data can be reasonably said to follow the normal. That's what the nearly normal means, is does your data, can you reasonably say that the data follows the normal? And a lot of times due to the large enough n, it does. On the 2 sample T, we have the independent means. And this one's really easy. It's just when you have these 2 groups, does the mean of somebody's score who attends the review depend on the mean of someone's score who does not attend the review? And the answer is no. Your score, if you attend a review, is not going to be somehow controlled by someone who doesn't attend the review. So the 2 groups are independent of each other. There are instances where the means are not independent. Think about if Brian goes on a diet. I don't know. then Brian's before weight and his after weight are going to be dependent. If I start at like 180, that's going to be a different end weight. If I start at 280, that's going to be a different end weight. So the start, like the average what people start at, like if you take 10 people, the average weight they start at is going to somehow dictate to a certain degree the average weight they end at. If they start at higher amounts, they'll probably have a bigger loss than if they start at lower amounts. So when you say the two means are independent, in this class, we usually hold to that. We don't do what's called a dependent or paired t-test. But the independent means whatever's going on in this group is not, or whatever goes on for this mean is not going to actively some way tell you information about the other. Another favorite example I like to have for this one is think about Kaplan. Like we have a before and after. It's a classic way of doing a dependent. Like you have people before they go to Kaplan, and then we test them again after they go to Kaplan. So we would expect that the mean after is higher because your score after Kaplan would probably depend on your score before Kaplan. A testing, if you want, Kaplan's a testing thing, so they'd help you get better at your tests. Well, that would not pass the independent means because people's after score would depend on their before. But if we're doing people studying for the review, did you attend the review or not attend the review? You might say, but wouldn't the people who attend the review get higher scores? Yes, but their scores would not depend on the people who don't attend the review. So depend means like in some way the other group influences the group. Okay, so now we have the last one here, the chi-squared test of independence. And the chi-squared test of independence has with it expected cell count. Oh, really? Can we do this? Look at that. Perfect. Expected cell count is greater than 5. And so when you go do the expected cell counts are going to be row total times column total over grand total. And you are given that formula. So if we have 100 people here, 20 people here, 10 people here, 110 here, 120 total. And you would see numbers inside of here, something like, let's say 7, 13, 97, and 3. I think that's right? So you might say, well, Brian, we do not pass the expected cell count because of this. No. That is an observed. That is what you see. Everything inside of here is an observed. Expected cell counts are going to be the following formula. They are going to be row total times column total over grand total equals expected cell count. And the easiest way to figure out if we pass is to take the smallest one, the smallest row, and think about it, because you're just doing the top of the equation, make it the smallest possible. Smallest row, smallest column, divide by the total. I think I've done all the math correctly, or those. And so let's see if we pass. I think we don't. So you thought we failed, you're right, but for the wrong reasons. And so we divide by 120. You would only expect 1.66 there. So you'd only expect 1.66. You saw a lot. So that was very interesting. But now we do not pass the expected cell count, and you can always just check the smallest one. So we could change the numbers right here. Here we'll just do a nice easy one. This is one of the easiest ones to solve if I do this. And so you could see, watch out, someone might be like, Brian, we fail. I'll write the numbers here to finish. And you might see 80 here, 20 here, 20 here, 80 here. But think if everything's like half, well, this would be a half of a half. This one's very nice because all the formulas, when you do the expecteds, turn out the same. You don't usually get that. It's very rare. So you would get everything as 100 times 100 or 200. So when you solve this out, you should get 50. There you go. And so we actually pass. Well, they're all greater than 5 up here, too. I should have done something more trickier. I should have done something like, because these are just what you see in the data. This is called the observed. What is in the table is the observed. These are the observed values. So the observed is what you see in the table. The expecteds are found via the formula. Make sure to do the exclamation before it, and that'll tell you your points right there. Hopefully I didn't write wrong. Not the first person to do that, so I might have written it wrong in the announcement because maybe I wrote it wrong. So that's expected cell counts greater than 5. This one would pass because all the expected cell counts are greater than 5. It's not failing because of the 1 right there. And then now the last condition is counted data. And actually, this one is super easy to check. Literally by virtue of it being a contingency table, it passes. But counted data means two categorical variables. It's like CC, not QQ. But literally, the counted data literally means you have two categorical variables. So by virtue of it being a mosaic plot or contingency table, that's called the mosaic plot, down here called a contingency table, you would pass the conditions right there. So that has got it. We went a little bit long on this section, but these are kind of the basics of statistical testing, and we did the conditions. So I should mark here the conditions. How long ago was the conditions started? So good to see Amelia right there. Let me go 10 minutes previous, and like hopefully I put a good timestamp in here for this. Need to check it later. Okay, so conditions for tests are chapter 13 through 19. Conditions for tests and intervals. I kind of just did some conditions. We'll take a quick break. Be back here soon. Bye for now. Let's go like 5-10 minute break. What's up? What's up, Drew? Good to see you there. Let's do another topic. My eyes are just blurring today. My right eye's blurring. That's not good. Okay, what should we talk about now? We've already done some big topics. So let's think about another topic right here. What would be another big... Hey, what's up, Grace? What topic should we do? Do you have a topic you want us to do? We've already done exam 3 formula sheet, chapter 13, 14 conf rules. We did error and power, statistical tests, conditions. I need to look to see when we did conditions, but we've done a lot of the things, a lot of things covered so far. So try to think what else we could cover. What else is there? We could do example problems or something like that. I don't know. What topic does anyone want to hear about? It's like there's only so much to cover. Let's go look at let's talk about review materials. Well, it's not gonna be a full section. Sure, why not? Let's talk about review materials. This section will be called test 3, exam 3, how to review. Okay. So we're talking about how to review for the test, and I'm going to give you my tips. Well, first off, you're watching this video. If you notice, the videos have timestamps. I add in these timestamps so you can quickly navigate the videos. We have a little fun between. We talk, we enjoy, we relax. So you can use the timestamps, but I'm going to start dropping some playlists in here for you. So playlists are going to be your best friend because the playlists, and we'll drop them. Exam 3, test 3. So here is test 3 concept review. And here is practice test 3. Oh, that's too many right there. I thought it was exam 3. Exam 2. Test 3. Oh, I wrote out 3. Test 3 speed runs right there. Let's open a new tab. Test 3 review videos. There's that. Test 3 review videos. Why is it test 3 review? We'll double check before we send that out. And test 3 assignments. That one's old right there. I don't think I show that one much anymore. So let's go over here. And there's the first one. So we kind of did this already today. This is the nearly normal. Well, trying to get to reload the link at the top. There we go. So this is concept review. Great playlist right here. Walks through the 4 steps of hypothesis testing. One thing you can do is you can actually use the Ask Assistant on it. You can go ask questions, and you could say, what
is one proportion?
Oh,
we'll come back to that in a moment.
Full screen.
We'll do that one as a review question.
Go back to
and
default
this is
view.
One mean.
And let's go back
so this
to the
is
ask
one mean
Stop
right
talking, Brian, please. Ask questions. Go into ask question this time. And let's go right here and say, what are the 3 conditions for testing a proportion? And let's see if it gets it right. It should say random, 10% success failure. Nice job. Look at that. What are the conditions for the chi-squared test of independence? I think this is really neat. It's using my video as the training data, and it got it. Did it get it? Yeah, random 10% expected cell count and counted data. This is a slight error. The independent, that is an error. So you got to watch out. You have to know how to check stuff, but make sure to check out. And I think it's really good. What are the conditions for the 2 sample T? Let's see, it should say random 10%, nearly normal, and independent means. And the last one should be independent means. There it is. And there you go. And they even mentioned the central limit theorem right there. Really good. And all the things I think I mentioned in here, going through the ideas of it. So you can ask questions. You can see if you know the things. Quiz me on this. If it does this, which Gemini can do, can it do it yet? Can it do it within here? Oh, it did it. Wow. Okay, let's see. So when conducting a 2 sample t-test for quantitative data, what is the required condition regarding the distribution of the data? So it said it's nearly normal. Well, I don't know why it highlighted the answer. B. So let's see. Correct. That is neat. Okay, so that's really cool right there. Let's go over to another video right here. We've got testing a mean right here, so you can see how this is done. And a lot of people wonder about this last one right here, where we find the p-value. So let's say we are stuck on this, and let's go to ask questions. And let's say, how do I find the p-value for the two-sided alternative using the output in this video? So a lot of people get stuck on this because this is the does not equals test. I'm going to start highlighting things here for you to see. But this test on the screen has the does not equals right here. That is the does not equals by virtue of greater than absolute value of t. This is the greater than test below it. So that's the greater than, this is the less than. And the greater than is when you shade to the right of it. The less than test is when you shade to the left of it. And the does not equals test is when you shade both sides. So if this p-value down here is 0.0033, then this one, good to see you, Austin, is 0.0066. This one right here would be the other side of the curve, 0.9967. So, of course, it's 67, right? But notice the relationship between the less than and the greater than up to 1, and the does not equals is 2 times the smallest. So hopefully it would say this, that they have relationships, and I don't know if it'll explain it. Oh, wait, look at this right here. It literally did it. Now, it got the number wrong because it doesn't hear the point, might be doing as a percent right there. But identify the one-sided p-value. Look for p-values prior for the greater than and less than. Determine which of these two p-values is smaller. Simply multiply the smallest p-value by 2. That is exactly what we said. And it's kind of crazy to me that AI can basically get these things right. And that is how it is solved for this question. That's not traditionally how it's solved for, because unless you have output or something, we just want you to understand the concept here. So it's a conceptual question of like, hey, how is this p-value found from the other ones? Like if you know one p-value, you can find the other ones. Statisticians would just use statistical software to find p-values most often, but then you have to understand where these p-values come from. Maya, good work right there. And so now, here's the second playlist. This is the playlist. Let me X out of this. So this is the practice test playlist. There's the practice test playlist. Now we get to the speedrun videos, some of my favorites. And I would say start watching these. So speedrun. Speedrun videos are a bunch of fun right here. Starts out the epic. And you can go through here and learn about this. And probably you could do the ask and say, love the comments on the video. It's always fun to see. And I don't think I added in this. I think these are automatically entered in. Maybe I went through and added that. I can't remember if I did. Did you start a video? I did. That might be me. Well, good for me for adding it. Let's go here and say, how do I get Gemini? So it should just be there. If you scroll down and you just go to ask questions, you just go to the video and you go to the view more. It's supposed to be native to it. Maybe it's a Chrome thing, but it should be there. And then you can just say like, what are the 3 big ideas from this video? So I wonder if it's going to give us the 3 big ideas from this video. Now, you have to make sure sampling distributions, well, that's from test 2. Means and standard deviations, confidence intervals, and margins of error and precision. Give me 3 questions on confidence intervals. So give me 3 questions from confidence intervals on this video. Question number 1, there's a 95% probability that the specified interval you calculate contains the population mean. Oh, it's asking what does it mean? What does it mean to be 95% confident? It means with repeated sampling, 95% of 95% confidence intervals contain the truth. And I actually just saw that in the video. That's where I'm talking about it right here. 95% of 95% confidence intervals contain the truth. So the first question is B. The second question is going to be, when checking the success failure condition for constructing an interval for the population, what must be true? You must have at least 10 successes, at least 10 failures. You must have at least 10 successes, at least 10 failures in your sample. NP hat is greater than equal to 10. NQ hat is greater than equal to 10. So that is answer A. And then the third question right here is going to be confidence versus precision, which is a great question to ask. What is the relationship between the level of confidence and the precision? As you get more confident from 68, 95 to 99.7, more and more confident, the interval gets less precise. So 68, 95, more confident, less precise. Precision means a tight interval. Like if your parents say, tell me precisely when you'll get home, you'd be like 10 to 10:05. And they're like, more precise. You're like, exactly at 10 when the clock strikes 10. So as your interval increases level of confidence from 90 to 95, the interval becomes it becomes less precise. As you increase the confidence, the interval remains nope. As you increase the confidence level, the interval becomes wider, which decreases the precision. Yes, that is true. Those are good questions. I'm not even joking. Those are kind of what we write. Correct? You got all three? Hopefully I'd get all three. I hope so. And it's best if you know the answers before clicking them. And then also, I think it might even give you links to in the video where I was talking about confidence versus precision right here. So you can see where I'm talking about the intervals and what it means to be 95% confident. So we should see at this point I'm drawing the intervals. So it's really, this is actually a great way to review if you ask me, because if you get it wrong, you can see the success failure condition right here. Really great way to use it. I wish you could then track your score on the videos or something. I'd probably use this and be like, review using the videos. If there was a way to do it, I would do it. But it doesn't track it really as far as I know. So then you have this test 3 playlist review. Got a lot of different videos in it. It's maybe just a bigger one. I'll drop it if you want it. But this is the confidence intervals and test with proportions. Oh, that's when it was... Chapters are just weird. This video is from 10 years ago, isn't it? It is. I made the video a decade ago. So, gosh. Big playlist. The first videos I ever made were in 2012, I think. So we go back to the start of the channel. And that's about it, because then we got one more playlist. Do we test 3 review videos? Another review playlist. Okay, review playlist. There it is. There is all the review videos, and we've got, I don't know how much more there is to review. That's the problem I'm running into right now, is when you think about how to review, you want to just kind of use the resources out there. You want to go to the review page, review 3. The problem is it broke a lot of my playlist links. I need to look into fixing that. But review 3 is now in the chat right here, and I think we might come back and stream later. We're going to come back and stream for the Kahoot, but I have a lot of material out there, and I don't know what else to cover because I have practice problems. I've already mentioned the video, but I'll send out some announcements and reminders. But I think we've covered the vast majority of the material. So with that, we've done a 3-hour stream right now, taking some breaks. So we have a good 2.5 hours of material in here. I think we'll end for right now, and we'll come back later. So as we like to say, bye for now, everyone. Bye.